director of the Black Hole Initiative, and it's a great pleasure on behalf of all of us PIs and postdocs and graduate black holes in MUSAC. So it was 9 years ago that we began this voyage of trying to assemble the various fields of astrophysics, theoretical and observational, of mathematics, of fundamental physics, of history and philosophy of science. And it was a great gamble. We didn't know that it would work to bring them together. We knew that each of these areas was prospering, that so many of these different fields saw black holes as a riveting central preoccupation, raising fundamental questions for each of the domains separately. But it was a hope that we could begin to combine these efforts in ways that would do something specific and more than the several pieces in isolation. And here we are, 9 years later, from the planning of 2015 to 2024, with the great good support of the John Templeton Foundation and the Gordon and Betty Moore Foundation, support of Harvard and the Center for Astrophysics, that we've begun to see really the fruits of that combination of concerns, and across many of these different domains. Black holes are having their moment, as they are wont to do, in each of these areas, and we've begun to be able to do things that was hardly imaginable some time ago. We've begun to be able to do simulations across different scales, and there's a tremendous effort to try to combine horizon scale physics, Bondi scale physics, galactic scale physics, in ways that will help us understand the composition and evolution of not only black holes, but galaxies and star formation and much else. It begins to bring in all the areas of physics, and look forward to expansion there. We've seen a huge exploration and application of the holographic principle, of notions of entanglement, of the relationship of quantum and classical physics, from full-on string theory through applications of quantum mechanics in its more specific Hawking-like relations to the horizon. We have thermodynamics explored in a myriad of different ways. And in the observational study of black holes is at an extraordinary moment, whether it's contributions by the JWST or the new timing arrays and pulsar results, the fantastic efflorescence of the age of interferometry across so many domains, including LIGO, the Event Horizon Telescope, next generation Event Horizon Telescope. All these efforts have begun to pay off in not only current results, but in amazingly exciting future domains of application. And then the history and philosophy of science has begun, I think, in a way that's quite unique across the domains of science, to be able to integrate in a successful way with the various efforts, whether they're observational or theoretical. And we have not only been spared the culture wars of decades past, we've actually had productive contributions in everything from questions of governance to epistemology, to how we get and understand the specificity of astrophysical knowledge, the role of imaging and images in astrophysics, and around black hole knowledge. All of these have contributed to making this a really remarkable moment. We see, for instance, the rise of photon ring science, where astrophysics, philosophy, observational physics, interferometric plans, space science, all of these are coming to bear on understanding the depth of what might be the holographic aspects of the photon sphere, all the way to trying to actually detect it, measure it, and use it to make a direct determination of the spin of black holes, which would be an extraordinary thing. For all these reasons, it's an enormous pleasure to have you all gathered here today. I look forward to hearing the talks. I look forward to our conversations at meals together, at coffee breaks, and taking walks. We've had beautiful weather planned for you here in Cambridge. And it's really a pleasure to welcome you, to thank our administrators, Nicole and Jesse, who you'll see around and who have done a fabulous job of organization. So, welcome to black holes.
Hi, everybody. My name is Helen Meskhidze. I'm a postdoctoral fellow at the Black Hole Initiative here, and I'll be the chair of the next session. It is an absolute honor to introduce John Mather, who will be our first speaker. Dr. Mather is a senior astrophysicist in the Observational Cosmology Laboratory at NASA Goddard and senior project scientist on the James Webb Space Telescope. You may also know him from his work together with Dr. George Smoot on analysis of data from the COBE satellite, which of course won the Nobel Prize in 2006. Dr. Mather's talk today is opening the infrared treasure chest with JWST. Please join me in welcoming Dr. Mather.
Well, good morning, and thank you for the invitation to come. I think I need some help getting the slides up. Is this microphone working? Can you hear me in the back? Okay. I want to tell you a little bit about the story of a giant project. There's the slide. Okay, thank you. I think most of you have probably seen in the news almost all the results I might have to show you, but I thought I'd concentrate on how did we do it and a little bit about why we do it and what it takes to get a great project going. So there's the telescope, as you know, a 6.5-meter hexagon in space, unfolded after launch, after what seemed to be terrifying to the public kind of launch and process. My project manager was at the launch site. I sat on my sofa at home because of COVID. Nobody went to the launch site that wasn't obliged to. So keep down the risk. Anyway, there it is. By the way, I'm no longer senior project scientist. I've been succeeded by Jane Rigby, who's doing a brilliant job. So this started for me. I was invited to join the project in October 30th of 1995. So it wasn't even my idea that we should have this telescope. Other people had already started writing a book called HST and Beyond that called for this telescope, although they weren't nearly this ambitious, and called for the technology, anyway, for observing exoplanets like Earth around stars like the Sun, because they knew that would be a good, hard project to try. Anyway, there it is. Took about 20,000 people to do this, and it's available for all astronomers. I guess you probably all know that we take proposals once a year, and that they are reviewed in a dual anonymous fashion, so we don't know where you are or who you are when we read the proposal. So that means about 10% of the winners are headed by graduate students. So there's hope for us all. So why do we do these things? I'd like to list the major questions of science that we can partially address with our kind of work at NASA. Where did we come from? Of course, that's a pretty tricky question because we don't even know what "we" means yet. The cosmic history we have begun to work out, as you know. The public wants to know, are we alone? A lot are convinced that, yes, surely they must be there because we see them in the movies all the time, space aliens. A major scientific question is, well, how did life start? And is that something that's always going to happen, or is it a very unlikely event? I'll give you my personal guess, which is that whenever there is a nice warm ocean, there will be the beginnings of life, at least with metabolic cycles of chemistry and probably going on to some form of life. But most likely, it's pretty unlikely for it to reach the kind of intelligence that we have anytime soon. It took the universe 13.8 billion years to make us, and we've only been here a short time. So if you're looking for statistics, probably aliens out there are unusual that we could hear from. Okay, how far can we go? Not very far, unfortunately. So people know what did I do? I pushed a button. This is the classic chart that showed the universe is expanding. People have misinterpreted all these charts and the stories of the expanding universe to say the universe was compressed into a point. I've heard it from countless members of the public that heard there was a singularity. And they don't know that a singularity means a neighborhood of a point, not the point itself. So anyway, we know this story. Hubble got the expansion rate wrong because his distance scale was wrong. We're still worried about the distance scale even now because we have two measures of the expansion rate from the geometric method based on cosmic background fluctuations and interpretation, and this one a photometric method. And they still don't agree, even after all these years. But now, and it's always as 5 sigma effect. So anyway, this is the Kobe satellite that was mentioned earlier in the introduction. This was proposed in 1974. When I was just 6 months out of graduate school, we started writing on this proposal based on my failed thesis project. So if you're a graduate student, failure is not so bad. You may learn something and try something. Although at the time my thesis project failed, I thought, this is too hard, I'm never going to do that again. So I moved to New York and got a job with Pat Thaddeus, who many of you might know because he was director here of the CFA after that. Anyway, we proposed this, it went up, and it did work because real engineers made it work. And so that's a long story there that you all know. Stephen Hawking said that was pretty important because that explains why we're here. If we didn't have those spots in the early universe, we would not have the instability that would produce galaxies, stars, planets, and people. So we're here because of those spots. And now we also know that a lot of those come from dark matter, and the shape and the statistics are determined by dark energy. So there's one heck of a lot of information in this. And when we started our proposal in 1974, none of that was even a hope. Nobody had any idea that we had standard equations that would lead to a standard model with about 7 parameters and a brilliantly accurate fit. So I had no clue. All of us thought, well, we just have to measure the best we can. And at the time in 1974, we had hopes for better technology, but it was pretty elementary at the time by comparison with what we now can do. So there's our great telescope in space, 6.5 meter primary. We have 4 instruments on board. They cover the entire wavelength range from 0.6 to 28 microns with cameras and spectrometers. And in particular, one of the instruments, the near-infrared spectrograph from Europe, includes a micro-shutter array which allows us to choose 100 galaxies and exclude all the light from everything else. So you get 100 spectra of galaxies at one time. It's a very powerful instrument, and a pretty large fraction of our observing time goes into spectroscopy for that reason. Operations are at the Space Telescope Science Institute, which means you can get all the data from our archives as soon as they are ready. Some of the data are posted immediately, and some have exclusive access to the principal investigators for up to a year. So that's how that works. It was launched on an Ariane 5 rocket from French Guiana on Christmas morning of 2022. So it's 2021, sorry. It's almost anyway, people to thank. These are the project managers that I worked with. Bernie Siri, the first one. Phil Sablehouse, who got us to the point where we knew we didn't have enough money. And so he was then replaced by Bill Oakes. But basically, they were both, all of these people were brilliant. Scott Willoughby at Northrop Grumman led the main contract effort there. And so these 4 people are the technical wizards who organized 20,000 people to do the job that I've shown you. Here are 2 other people, Senator Mikulski and Charlie Bolden, our NASA administrator, around 2011, had to deal with the fact that we did not ask for enough money. So what do? Well, first we embarrassed the senator. And then she says, please fix this. And so what we had to do was to get outside reviewers to say, yes, it's a good project, did good work, did not ask for enough money. And that was the main upshot. And so that was enough for them to say, okay, Congress, can you please finish this job and please get us the more money? So this is just a reminder that it's not always good to have a low budget, but you can get rescued sometimes. James Webb, by the way, when he went to Jack Kennedy with a plan for Apollo, he was in the taxi cab and he thought, I don't think this is enough money. And he doubled the budget on the way to see the president. And this is before we had spreadsheets to prove that was not right. So he was right. If he had not done that, that would have been a national disaster. Can you imagine not asking for enough money on something of the scale of the Apollo? Anyway, so thanks to them, we have what you have seen in the press. These are the 4 instruments I measured: near-infrared camera, near-infrared spectrograph with the micro shutters, a mid-infrared instrument, and the fine guidance sensor and near-infrared slitless spectrometer from Canada. So they all can work, and we have multiple different ways to do spectroscopy. And once in a while we say, do they all get the same answer? And mostly they do, which is good. Go on. Okay, computer. So we had to invent new technologies. Here they are, not to tell you any great detail about them, but especially the new, better detectors we had to get. We need to get a cryogenic integrated circuit to run them. We had to get a cooler to get one of the instruments down to 7 Kelvin, which, by the way, means that stored helium does not limit the life of the observatory. We had to invent the micro shutters and, of course, learn how to focus the telescope after launch. For a small historic note, we had to learn those algorithms when the Hubble was launched out of focus. So how do you find out what happened then? NASA ran a competition. Who can tell us the right algorithm to figure out what to do about the Hubble out of focus problem? And the winner of that algorithm is basically the same one that we use today to focus the telescope when it slightly drifts out of shape. Because now those 18 hexagons are not guaranteed to be in the right place. Now we have to adjust them, or we check them about once a week, and usually can let them sit there for 2 or 3 weeks at a time before we have to adjust them again. So that was a huge technical accomplishment to get those ready. And we basically set out and said we can't even settle the design of the observatory until all of these are at what we call TRL 6, Technical Readiness Level 6. So when we knew that they could be done, then we said now we can choose the design. So that was back in 2002. A little bit about risk, because some of you are going to take on a new satellite mission proposal. How do you know that it's going to work? Well, you don't always. But what can you do about it? Well, I put up there at the, I say, Murphy was an optimist. He said things would go, if things can go wrong, they will. In our case, so we had one item that failed after the last test. And that was a bit of a surprise. We were able to send it back to the manufacturer to get it fixed. I have put on informal risk assessment because we are can-do kinds of people. And if you want your project to work, you cannot be a hands-on, can-do person all the time. You have to have the grouchy person who says, that's not safe enough, that's not good enough. Too many of my people and friends have fallen off a ladder. Some of them have been injured riding bicycles, one killed riding a bicycle. So if you do not do this right, you will crap out one way or another. So there's no such thing as why don't you take a chance on skipping this test. If you do not test this thing, the universe will get you for that. I used to say God will get you for that. I wrote this one, never trust the boss, especially if you are the boss, because this had happened to me. There were a couple of times I woke up in the night realizing that the Cosmic Background Explorer instrument that I had designed was not going to work. I had made a mistake. And I had not set up a process to have somebody check my work enough. So nobody knew except me that that was a mistake. Well, that's pretty darn scary, and do not do that. If you do have a chance now to do that better. Do not trust yourself just because you think you're smart. If something matters, you better have it done at least 2 different ways. They made that mistake with the Hubble mirror. They had 2 different ways, but they chose the wrong one to believe. For the Webb telescope, we said, we better make sure everything is measured twice in different ways, and the one that we use to build something cannot be the same one that you use to verify that it's correct. So anyway, so those are things to remember, and best of luck. If you want to know the details about how to manage risk, we have, of course, a risk management plan when you can Google this title and find it. So the upshot was you need a lot of tests, as well as a lot of grouchy people to catch your mistakes. Oops, what did I do here? I did the wrong thing. So I do not know how to get back to my slide set. Can somebody help me with the slide set? Anyway, what I was going to show you was a picture of the telescope hanging in the vacuum tank in Texas.
Which one are we looking at here? Sorry,
Yes, this one over here, that one. That's the exact one. Mm-hmm. Thank you. So here's the telescope hanging in space in the vacuum tank, looking up. You can see it barely fits in the vacuum tank. We had to suspend it from the top on giant rods. Had to suppress vibration because we needed to measure nanometer level vibration, nanometer level accuracy in the presence of micron quantities of externally imposed vibration. So this giant test took us about 6 months, and the Hurricane Harvey hit right in the middle of this test. So quite a heroic effort. Many people were involved in that. And anyway, we learned that we could focus it in flight, and we tested all the algorithms to move all the 18 mirrors, and it succeeded. But it's an immensely difficult thing to do. So when you're thinking about satellite missions of your own, a proof that the thing works before flight is pretty hard to do. And definitely you will have somebody who complains if you don't have a proof. So anyway, what did we see? Why do we observe infrared? Number one, because dust clouds are opaque, but you can see through them if you use longer wavelengths. Light's a wave and diffracts around dust grains. Number two, because things are cool, and sometimes you can't see them very well at visible wavelengths, but you can see them better at mid-infrared wavelengths. So here is a debris from a set of stars that are blowing up. One particular one is blowing up now, producing all this cloud of dust and cool stuff. Calculation says there are really 5 stars in the middle, although you can only see 2. So that's why there's this complex shape. So this is the part of the story of how come we have people, because this stuff coming out of stars is the dust that gets recycled into stars like the sun, planets like the Earth. The third reason, of course, is that space is expanding. We need infrared light to pick up the light that used to be ultraviolet or visible. So this is, and then what did we see? This is my favorite picture from the whole mission already. This is the first one we put out. It's July 11th of 2022. And it has signs of fascinating things, the beautiful things with the spikes sticking out of just old stars, plenty ordinary as far as we know. The galaxies in the middle, big fuzzy ones, have enough gravity to activate Einstein's gravitational lenses, and we have dozens of distorted images of distant objects way out there, some of which are quite highly magnified. So anyway, the fact that things can be highly magnified was something we anticipated, but I thought, well, it's not likely we'll ever see any. But here's a sketch of one. The red curve on the right is called the critical curve, or also called the caustic curve, and this place a region in the sky where the magnification is basically unlimited. So there we have at least one observation of a single lens star at high redshift, where it just happens to be lying on the critically magnified curve. So far as we know, that one is an ordinary star. It's a good old B star, nothing special, but the fact that you can do this is remarkable. So we have catalogs of hundreds of gravitational lenses, and they are one of the main observing programs. We, of course, look at places where stars are being born in these beautiful dust clouds, and the mid-infrared allows us to see better and see inside. One of these days, the people that make models of star formation will be able to tell you how it all works. But you can see there's a wind blowing, compressing the surfaces of the clouds. There are vapors coming off. The heat is vaporizing the surface of the clouds, and it's a marvelous study in hydromagnetodynamics. So one of the coolest things we got is this one. It's an observation of a star forming in its disk, and we're seeing it edge on. So right square in the middle of that hamburger, and you see in the middle of the bun, is presumed to be as a star that's growing. And it's invisible because of the dust, even at these wavelengths. If we were to come back in a few 100,000 years, it might be that all the dust will be gone. The star system will now be a star surrounded by planets, and you should be able to see them a little better then. So you see also this rather common form where jets of material are coming out. So there it is to be followed up. We've done, as you know, many planetary observations, and the ones that are most interesting to many people are the transit spectroscopy measurements. What we've seen so far is that the small rocky planets, small enough to be like Earth, do not have atmospheres. The ones that we're able to observe are the ones that were orbiting M stars, which are very small and rather hostile. The planets are very close to them, and the stars are very active with flares, so presumably that's able to rip the atmosphere right off a small planet. The hope and expectation is that there are planets more like Earth around stars like the Sun, but we can't tell because we don't have the technology is not good enough to make that analysis. We do, on the other hand, see that other planets with atmospheres are there, and they have. Okay, so I think this is my last chart, just to say that there are lots and lots of sources of information online. There are lots of things we could say about future telescopes, but I think my time allocation is about up. So let me just wind up and say there are a few things that are really interesting to me about black holes that are coming from this. Well, number one, we've already seen a twin black hole at a high redshift, around 10 or so, which says rather large black hole masses already existed very early. So that's a puzzle for all of us. How did that happen? So from what I hear, it supports the idea that those black holes grew from smaller black holes merging. So, okay, where did the smaller ones come from? Are they primordial, or were they all formed in an early burst of star formation? So that's open question right now. And to me, one of the other questions that's still open is, so, well, what's the dark matter? And so since we've been so far unable to detect its presence in any laboratory experiment, could they be primordial dark holes of some sort? And so it's presumed to be, well, for a long time, I believed the stories that there were no black holes of the right sort, or we would have noticed. But now I'm hearing, well, they could have escaped. So if they could have escaped, that's a great challenge for us. Say, how could they have formed? Could the Big Bang have produced them, or would they all formed later? And how did that happen? So, and we thought we had a complete explanation that they could not be baryonic because of various things from the statistics of the CMB, but maybe they are anyway. So there's some puzzles to be resolved. So plenty of things for us to work on. Thank you for inviting me to come. I'm eager to learn more about black holes from you.
Okay, we started just a few minutes late, so we have about 9 minutes for questions. I'll bring you the mic.
Thank you, that was great. I have kind of a historical question. You said you kind of joined in 95, right? And JWST, or whatever it was called, had already been, under consideration before that. Mm-hmm. I'm just thinking, the first exoplanet was only discovered around 95, and the fact that black holes are so important for galaxies, the M-sigma relation came around 2000, or maybe a little earlier, 97, in terms of luminosity, black hole mass. But all this is in the future. So at that time, say 90 to 95, what was the big hope that people had that JWST will actually do?
Well, I think people recognize the big mysteries. The book is called HST and Beyond. It's beautifully written committee report. You may not always expect a committee report to be poetic. But Alan Dressler was the chair, and it's a beautiful thing. I got goosebumps reading it. So all of the great mysteries that we have today were already imagined then.
Including the origin of, life?
Yeah, I think they obviously was a question, where did the planets come from? We didn't yet know how soon we would find a few of them. We also didn't know about the dark energy, and so we didn't know how to calculate the properties of the first galaxies we were going to hunt for. So we had a free parameter. What's the acceleration parameter? So a lot of simulations were run that we didn't know what to simulate. But we promised that if we could build this telescope, we would discover wonderful things, and which is true. So, yeah. Okay.
Yeah, hi. One of the things which, when JWST was being built, I heard a lot about was looking for population 3 stars. What is the current status of that?
Okay, I don't think we can see them directly very much. What's turned out to be obvious, what was obvious at the time, if the population 3 stars are indeed high mass, they have a very short lifetime, and they go poof and poof, and suddenly they've blown up, and their nuclear products are distributed everywhere. so now the job is, can you find a very early galaxy that has any signs of not being enriched with lots of heavier elements? And so there's some progress. I do see it in the news occasionally that something's been found with very low evidence of heavier elements, or that represents a particular class of supernovae, because the distribution of heavy elements depends on the kind of star that it was that blew up. So there's evidence, but I don't think we're ever going to see an individual high-mass primordial star, population 3, at high redshift. There's some signs that, of course, maybe you can see a very low metallicity star right here locally, and a few of those have been found. And we got to study them, but they're not easy either. Yeah.
So for those of us who are thinking of these new missions, what I note about JWST is that it took a long time, probably rightfully so, but it also took a lot of money. And looking back, what would you have done differently?
I don't think I would have done anything differently. I started off saying, well, this is so important, I'm going to work at it. I do not know how long it's going to take or how much it's going to cost, but this is worth it. And basically the entire astronomy community could participate in it. This is going to be a telescope project that serves all astronomers. So who's going to be against it? So there's a hope that even if we run into trouble, we'll still be able to succeed. So we'd already at that point rescued the Hubble by fixing it. And so we sort of knew the public enthusiasm about this kind of science was high. So there's a reasonable chance to get Congress to do what would actually lead to this. So we did, on the other hand, start off under the leadership of Dan Golden, who was urging us to find a way to do this project for much less money than everybody else thought was possible. So our attitude was, well, okay, boss, we'll start. We don't believe this can be done, but we'll keep on going. And so eventually you get to where the budget is not enough, and then you ask for help. Ideally, you would say in the future we are a little smarter about planning budgets, and we won't all start with the boss trying to press down the scale of the budget. But in the end, it worked out. Here we are. So can't argue with success all that much.
Okay, great. Thank you all so much, and please join me in thanking Dr. Mather. Our second speaker of the session will be Mina Himwich. Mina is a postdoctoral fellow at the Princeton Center for Theoretical Science, and Dr. Himwich's talk is titled Celestial Symmetry Actions on Massive Particles.
Okay. Hi, I'll be talking about some work related to celestial holography that came out at the end of last year together with Monica Pate. I tried to keep, since this is the first session, I tried to keep it very general, so apologies for the experts. We can talk, I'm happy to talk more about the details after the talk. Before we get started, I wanted to thank the organizers for putting on this conference. It's really great to be back in Cambridge again and see so many familiar faces. And it's also especially exciting for me to be speaking right after John Mather, who I think the organizers didn't know. I actually first met as a high school intern, summer intern at Goddard, when he happily agreed to be interviewed for our high school newspaper. So I grew up in Maryland. Okay, moving to the talk. Today I'll be talking about progress along one avenue to trying to understand quantum gravity. So quantum mechanics describes particle interactions at very small scales, and general relativity, gravity describes gravity as the curvature of space-time at very large scales. And there are regimes where we think both of these are important, but our theory currently breaks down, such as around black holes, which I'm sure we'll hear about more later in the conference. So we're interested in trying to find a theory of quantum gravity, or a theory of what is the short distance quantum mechanical interactions and theory that reduce to general relativity at large distances. So today I'll be talking about one approach to answering this question, which is to study particle interactions and scattering in the theory. So in principle, if we want to study particle scattering in quantum gravity, we can use high energy particle scattering to probe interactions at short distances. So the way that this is set up is that we have some initial configuration in the infinite past, or in the past. It evolves over time and undergoes some scattering, and then comes out to some final configuration in the future. So what we want to ask about the scattering process is, given an initial configuration, what does the quantum mechanical theory predict to be the final configuration after time evolution? And we assume that the particles are separated and don't interact in the infinitely far past, which is, we take the beginning to be the infinitely far past and the infinitely far future at the end. So in the context of scattering, the question of quantum gravity becomes the question of what are all of the allowed scattering processes in this quantum mechanical theory of gravity. And the problem is that in quantum field theories of gravity, the short distance or high energy interactions cannot be systematically predicted. So we need a different way to answer this question. So one way to make progress in studying these interactions is to use symmetry. So this is, again, a very high-level review. Here by symmetry, I mean just a transformation that leaves the laws of physics unchanged. And symmetries imply a conservation or time invariance of certain physical properties due to Noether's theorem. So one classic example is time translation symmetry implies conservation of energy. And in the context of scattering, symmetries imply that the final configuration is constrained to have certain physical properties, like the total energy, in common with the initial configuration. And also, it means that pairs of initial and final configurations can be transformed by symmetry into other pairs that also obey the same laws of physics. So if we know one set of configurations is a physically allowed process, we can transform it by symmetry into another one. Okay, so now I'll get into more details of the setup of scattering amplitudes. And also feel free to stop me with questions anytime. So in scattering amplitudes, we label the initial and final particles with their momentum. So this is a momentum space amplitude. They're in kets because we think of this as a quantum mechanical process. And the scattering amplitudes are just functions of incoming and outgoing particle form momenta. They also depend on their polarizations and other labels, but those will mostly be suppressed in this talk. So again, we need to specify if we have an initial configuration, there's some different probabilities for it to evolve to different final configurations in quantum mechanics. So we need to specify both the initial and final configurations here. And we label these in and out states by momenta that, again, we assume are separated. So we just list them in the initial and final states. So we can also think about amplitudes as S-matrix elements between in and out states. So we take all the in states, which are states or vectors living in the quantum mechanical Hilbert space, evolve them with the S-matrix, and then look at their overlap with the out states. And you can square this to get probabilities as usual. So in the context of amplitudes, symmetries are transformations that act on the in and out states, but leave the S-matrix invariant. So if we have a symmetry transformation labeled by this U, we can think about it as acting on the in and the out states, but also leaving the S-matrix invariant. Okay, so now I'll talk about how we can parametrize the in and out momenta in a way that can elucidate some nice properties of amplitudes. So I'll be talking about amplitudes in four-dimensional, so 3 space plus 1 time, asymptotically flat geometries. So massless particles follow null trajectories. So they have, therefore, momentum p squared equals 0. And so they can be parameterized by an energy and a direction or 2 angles. And if we think about massless particles traveling through space, and you can ask, where do they all go in the infinite future? Like if you turn on a light bulb, for example, and ask about where things go in the infinite future, that space is labeled just by all the directions that massless particles can travel. So it's labeled by the sphere, and the sphere is at infinity, and it's in the infinite future, and it's known as the celestial sphere. So null momenta are directed toward a point. Each null momentum you can think about as directed toward one point on the celestial sphere at null infinity. And usually we can think of spheres as labeled by 2 angles, an angle from the top and an angle around. Instead, we'll be using this complex coordinate z, which you can construct out of the 2 angles. And so you can think about the sphere as being labeled by z and z bar instead of theta and phi. Okay, so here's our form momentum for a massless particle. It's labeled by a sign for whether the particle is coming in or out, an energy scale, and then this direction vector, which is just a direction on the sphere. So this simple picture of massless scattering already suggests something interesting related to suggests the idea of celestial holography. So holography is the idea that you can have a quantum mechanical theory of gravity in some number of dimensions, which is holographically dual or equivalent to a non-gravitational quantum theory in fewer dimensions. So here we've seen already that four-dimensional scattering can be described in terms of these points. A massless scattering can be described in terms of points on this celestial sphere at null infinity, and it's defined in the infinite past and infinite future, which is a lower dimensional space. So 4D massless scattering is naturally defined locally on this 2D celestial sphere. Each bulk momentum corresponds to 1 point. And we also have the nice observation that 4D Lorentz symmetry, SO13, is the same as 2D global conformal symmetry, SL2C, on the celestial sphere, which preserves angles but not distances. And this suggests already that quantum gravity in a 4D asymptotically flat spacetime could be dual to a 2D theory with conformal symmetry or a 2D conformal field theory living on the celestial sphere. And there's a lot of nice evidence and work done in this direction. There are some reviews at the bottom of the screen if you're interested in reading more. And the idea is that 2D conformal field theories are really well studied, both in the context of the string world sheet and in phase transitions. So if we can use the power of 2D conformal field theory to learn more about the theory from in the 2D perspective, that we can go back and translate that to learn about quantum gravity in the bulk in 4 dimensions. Okay. So for massive particles, you can think about the same kind of picture where massive particles come in from the infinite past and go toward the infinite future, but now massive particles are time-like, and they go from time-like past infinity to time-like future infinity. And so now they're parametrized by a mass and a direction that involves 3 components. And time-like infinity is actually parametrized by a space-like hyperboloid, or Euclidean ADS3, not the celestial sphere. So massive momenta are again given by a sign epsilon, a mass, and now this direction vector p hat that involves a point on ADS3, which you can think about as these 2 angular variables, w and w bar, and a radius y. So n here is a reference vector. Good. So you can still think about like a holographic picture for massive particles. 4D Lorentz symmetry has a standard action on the Euclidean ADS3. And it's also possible to associate massive momenta with a point on the celestial sphere, or the boundary of ADS3, by convolving them with what's known as the bulk to boundary propagator. And but this convolution involves contributions from all massive momenta. So there's not a way to associate one point on ADS3 with one point, unique point on the boundary. So both from this picture of massive particles going to time-like infinity instead of null infinity, and from the fact that we can't uniquely associate a point on ADS3 with a point on the sphere, there's no analog of the massless relation between 2D and 4D locality. That is, if you have two massless particles that approach each other, whose trajectories approach each other in the bulk, the 2 points they hit the celestial sphere will approach each other as well. But that's not true. We can't do this for massive particles. Okay. I only have 10 minutes left. I'll try to keep going and see how far we get. So now I'll move to talking about a particular type of amplitude that we'll see are useful for understanding symmetries. Okay, so we're going to be considering the an amplitude with a graviton in the external state, and then looking at its low energy expansion. So looking at the left-hand side of this equation, there's an amplitude with particles P1 through Pn, and also a graviton in the external state with energy omega and direction q hat. And we can expand this amplitude just as an expansion in the graviton's energy omega. Here, kappa is like the gravitational coupling, proportional to the square root of g. And the leading term in this expansion famously is a pole, so omega to the -1. And then we go on from there. This is at tree level. So the leading and subleading terms take a familiar form. The leading term is due to Weinberg from 1965. So the term multiplying the pole in this expansion can actually be written as a sum of soft factors multiplying the amplitude without the soft graviton. And each of these soft factors involves the graviton's direction, q hat, the graviton's direction, q hat, its polarization, epsilon, and the momentum, pk, of the external particles. So the subleading soft theorem, there's a subleading term, and the subleading soft theorem is also familiar. And the same thing happens where you can factor out entirely the graviton's direction into the sum of soft factors, one for each external particle. And now it involves the graviton's direction, polarization, and then the angular momentum of the external particles. So one important idea that we've gotten from the past decade plus of work on this subject is that we can think about soft theorems as infinitesimal symmetries of the S matrix. And so we think about these soft factors, S, as enacting an infinitesimal symmetry transformation on the hard states. And so here the S can be labeled by the term in the soft expansion L, the K for each particle, and then they depend on the graviton's direction q hat. So you can think about different symmetries for different directions of the graviton momentum q hat. And it's been shown that the leading soft theorem is equivalent to supertranslation symmetry, which it generalizes translations to a different translation on every point on the celestial sphere. And then the subleading soft theorem is equivalent to superrotation symmetry, which generalizes Lorentz transformations to a Lorentz transformation at every point. And together, these form the extended BMS symmetry group, which has Poincaré, or usual translations, and Lorentz transformations as a global subgroup. And I should also mention these papers consider the massless case, and the massive case was done by Campiglia and Lada, I think in the same year. So the natural question is, what about symmetries from the further subleading soft terms, the higher terms in omega? So what we found was that the infinite further tower of subleading soft graviton modes actually extends a chiral half, chiral because we're looking at one graviton polarization at once, to an infinite symmetry that's known as W1 plus infinity. And this result, and the action on the hard massless on amplitudes with hard massless particles, or external particles that are massless, was derived in celestial holography by really exploiting the 2D conformal symmetry and the fact that massless particles are local on the celestial sphere. So the question then is, how do we define the symmetry action on massive particles without using 2D locality that we had for massless particles? And I can't go into the details, but the place where this comes up is just in the inner product of the graviton direction and the external particle's direction. So if the external particle is massless, the inner product involves the difference between the 2 points where the graviton and the external particle hit the celestial sphere. That goes to 0 as these angles go to 0. But if the external momentum is massive, then you can't talk about this inner product going to 0 as the angles go to 0 because it's regulated by this ADS radius y. Okay. So what we did in this work was to derive a symmetry action that works equally well for massless and massive particles. And here I'm just going to basically present the results. I have, I think, 5 minutes left. So to identify the structure of this W1 plus infinity symmetry algebra, we need to relabel the soft expansion by this P is L plus 4 over 2. So L, again, is the term in the soft expansion in omega. So we start with the leading pole at L equals -1, and then go on in integers. And that gives us P that starts at 3/2 and then goes up in half integers. So for massless particles, again, because the soft factors, these SKs, involve the external particle's momentum, they differ from massless and massive particles. The infinite tower of the further subleading terms, the soft factors, was known previously in the literature and takes this form. So here L is the angular momentum again. F is a combination of the graviton's polarization and direction. And you can define the symmetry action on the massless using the massless external soft factors by taking this integral transform, integral over z, which is labeled by a p and m. So basically the integral, the fact that we're integrating over a z means that this integral won't care whether things look local or not, since we're integrating over all these points z. But so these transformations are labeled by p, which is, again, related to the order in the soft expansion, and m, which ranges from 1 minus p to p minus 1, and there's a closed set of these for every p. So you can prove that these actions satisfy the symmetry algebra W1 plus infinity, which is here. This just tells you how to compose the generators. And this is an extension of the Carr-Poincare algebra. So Poincare would be at p equals 3/2 and 2. This is the leading and subleading ones, and the rest of this algebra extends this to its infinite symmetry. So for massive particles, we can now proceed along the same lines. But it turns out that for the further subleading soft theorems, again, related to this fact about the non-locality on the celestial sphere of massive particles, new soft factors need to be considered for massive particles. But they can be derived systematically from Lorentz covariance. So this is the result we found for the new soft factors for massive particles. And then using these new soft factors, you can define the symmetry action in exactly the same way as the same transformation of the soft factors, where you use the original form of the soft factors for the first few terms, but then beyond this sub-subleading term, you have to use the different form. And this form exactly is what gives you the fact that this form allows you to derive this W1 plus infinity algebra, and you can again prove that this symmetry action satisfies the algebra. Okay, so just, again, that was very high level. I'm happy to talk more about details with people who are interested. But just as a summary, I tried to explain that symmetries are an important tool for constraining scattering amplitudes in quantum gravity. And soft theorems can be equivalently thought of as infinitesimal symmetries of scattering. So in this work, we clarified the origin of this W1 plus infinity symmetry algebra from the tower of momentum-space soft theorems in a way that allowed us to treat massless and massive particles on equal footing. And we also had to develop a new proposal for the massive soft factors that was motivated by Lorentz covariance. So we found this, here I showed the symmetry action in momentum space, but it can also be transformed by this bulk boundary propagator to the conformal primary basis. And that's included in the paper. And we also showed that this symmetry action satisfies the W1 plus infinity algebra. So there's many future directions too that I think are particularly interesting and people are working on is how is the algebra corrected by additional interactions? And then also sort of in a different line from this work, is there a way to write a local symmetry action on massive particles using some other type of transformation? So I'll stop there. Thanks.
Thanks, Mina. Questions?
So what do we mean by a new proposal for soft factors? Like in the massless case, you can just compute it diagram by diagram or something like that, right? Like, is there, like, you propose something and do some consistency check, or you... Like...
Yeah, so I guess basically you can think about, yeah, you can compute them, but there's a question of what you want to call the soft factor versus what you want to call the rest of the amplitude. And this beyond sub-subleading order, or beyond subleading order, the amplitude doesn't split into just the soft factor acting on the amplitude. There's soft factor acting on the amplitude plus something else. And so you have some freedom in what you call the soft factor. And here we're arguing that because this soft factor corresponds to this Lorentz covariant infinite dimensional symmetry, that this was what we should think about as the soft factor for massive particles.
Thanks.
Yeah.
Hi, Mina. Thanks for giving a nice simple introduction. I think I followed a lot of it, but I'm going to disappoint you with a really dumb question.
Okay.
Right? So, you set up this scattering problem. Some number of particles come in, some number go out from infinity to infinity or whatever, fine. And then at one point you said, okay, now I'm going to put a soft graviton. That's where gravity was first entering the problem.
Yeah.
Except I couldn't see what was it that told the theory that this is gravity and not something else. Where did you tell it that it is gravity?
I guess, well, you just tell it in terms of the particles' quantum numbers. So we know that it's a spin 2 graviton, and it couples with the gravitational coupling. So
your definition of gravity is a spin 2 particle.
That couples in the usual standard gravitational coupling and doesn't have other charges. Yeah.
Okay, I didn't see that in the equations.
Oh, yeah,
Thank
sorry.
you.
It was, okay, well, it's back, yeah. It's going to take me a while to flip through back, but yeah, here. So the fact that this is a graviton means that you can expand this you get this expansion with the gravitational coupling here. And there's also this polarization, which appears in the soft factor.
And the Newton constant is somewhere in the kappa?
Yeah, it's here. This is a...
Oh, yeah, good. Thank you.
Great. Other questions?
Can these W1 infinity symmetries be understood from a purely classical perspective, like Bondi BMS symmetry?
Yes. I think you can think about just charges in general relativity, and Anna, who's also speaking here, has done some work on that. So, yeah.
Okay. Join me in thanking Mina then. Okay, our last speaker of the session is Niels Martens. Dr. Martens is an assistant professor at the University of Utrecht and an active member of the History, Philosophy, and Culture Working Group of the Next Generation Event Horizon Telescope. Today, he's going to be telling us about 10 plus ways in which the humanities and social sciences can contribute to black hole research.
Okay, thank you, Helen. Good morning, everyone. In this talk, I want to give you an impression of the work being done by the History, Philosophy, Culture Working Group, HPC, or HPNC, for those who might confuse it with high-performance computing. This is within the Next Generation Event Horizon Telescope Collaboration, or NGST for short. And I imagine for this specific audience, I don't need too much of an introduction of the NGST, so I'll keep that part of the presentation rather brief. So you'll be all familiar with these images of the black holes by the EHT. The technique being used here is that of VLBI, very long baseline interferometry. The idea being that there are lots of telescopes or arrays across the globe. Each pair of them forms a baseline. As the Earth rotates with respect to the target, you get different effective baselines. Each of them captures one Fourier mode of the image. Bring them all together in a supercomputer, and you basically have a telescope, this virtual telescope, the size of the planet, and together it constructs the whole image of the black hole. So yeah, as I said, what we're after is black holes. So the photons that reach us here can come from many different initial directions. Some of them will come from roughly behind the black hole. They'll be bent a little bit by the black hole. So it looks something like this. But there will also be photons coming from roughly our side of the universe. They go around the black holes. And there will even be photons that go around the black hole multiple times. And then you will, in a second, see an ideal situation. We would observe a very neat, nice photon ring, as you see there. And then, of course, you can combine all of these. And ideally, you would get a total image that looks like something which we'll see in a few seconds. Very beautiful, isn't it? Yeah, so we've seen the lowest order contribution. Ideally, you would like to see the photon rings, and we would also like to make high-quality videos of black holes. And the way to go about this is, over the next decade or so, build 10 or so dishes at strategic locations across the globe to complement the existing network. And when I say we, I mean this is a big chunk of our group, over 300 scholars from many different communities, physicists, mathematicians, astronomers, computer scientists, but also historians and philosophers and sociologists, etc., etc. This is our current structure with the management team. Many of them are present in this room. We also have 8 science working groups and an engineering team with 3 associated technical working groups. And one of the many ways in which this group collaboration tries to be innovative is by including scholars from all corners of the social sciences and the humanities. And not kind of on the sideline as passive observers who might kind of listen in or maybe join the group 10 years later. But no, we are a working group, a science working group, fully integrated right from the start. We are, well, technically over 100 people, but let's say 50, 60 very active historians, philosophers, sociologists, anthropologists, etc., etc. Many of us are here in this room. Now, typically in the early stages of such a collaboration, one lists all the goals, right? A wish list of all the science and engineering goals, and then prioritizes them in the science traceability matrix. And the idea here was not to only include science and engineering goals, but also to include perspectives from the social sciences and humanities, and that's what the HPC is all about. So we've decided that it will be smart to focus on 4 main areas. So foundations of black hole physics, collaborations, how to organize our collaboration, responsible, ethical telescope sighting, and also algorithms, inferences, and visualizations. So basically what I want to do in this talk is give you kind of a menu, a taste of at least 10 ways in which the social sciences and the humanities can and are currently contributing to black hole observation research. So let me just go through them one by one. Contribution 1, responsible, ethical telescope sighting. The history of astronomy is not particularly great in terms of always including the local stakeholders and treating them fairly, and we want to break with this tradition. So the idea is that our ethicists and sustainability scholars and anthropologists and astronomers, as early as possible, identify the local stakeholders and start a discussion, not with the aim of persuading them at all costs that we want to build a telescope there, but asking what would be like a mutually beneficial situation, going in with the idea that a no might well be an answer that we will get, and that is fine. Many of us are working on this in this room. There's Daniel Palumbo, Jaco de Swart, and I'm sure a few others, if you want to talk about this topic. The second group of our members, Foundations of Physics, or the more technical philosophers of physics, love to talk about the role of idealizations and abstractions in physics. In this context, it's all about kind of the gap between, on the one hand, the very formal, idealized, neat results, like the no-hair theorem, and on the other side, the very messy black holes we find in the wild. And so our philosophers of physics are trying to help bridge this gap, and one way this is being done is with the Foundation Seminar, which takes place every Monday here and has been doing so for many years at the BHI, currently organized by Helen Meskhidze and Prashant Ghosh-Lakota. Moving on to algorithms and the visualizations they eventually produce. One worry here is always that what we see in the eventual image might just be an artifact of the algorithm and not something that connects to the black hole out there. So we have a few philosophers of science who are experts in mitigating these risks, either via robustness analyses or convergence arguments. Right, so they might ask the question, is the black hole supposed to, or is the image directly supposed to represent a black hole? Maybe yes, maybe no. Maybe we should treat it as an epistemic tool, right? A tool that allows us to derive true statements about the target system. What is this tool? How to use it? How not to use it? How to interpret it? What justifies it? If you want to hear more about this, Jamie Elder, Yuri Stobachevsky, and Palumbo are sitting over there. So they can talk to you about these kinds of things. And then when you eventually have an image, there are a lot of choices to be made in terms of the public reception. And right, these choices might influence how these images are received by the public. So and I think our task here is to just make these choice is very explicit and list potential drawbacks and advantages of certain choices and make sure that we make the right choices here. So one thing to consider is, of course, like which color scheme do you choose? Which physicists might think, well, it's a very hot thing. Blue is the more natural color system, but for many people on the street, this yellow, orange, red might better represent how hot, how warm this system is. So, for instance, one of our members, Elizabeth Kessler, wrote a book which talks all about how the Hubble images, the color schemes there, connect to color schemes in American patriotic paintings and how this influences their receptions. So our main point is just to be clear of such connections and make these decisions explicit rather than implicit. And a related question is, does one decide to produce one image for the scientist and another one for the public, or just one image for everyone? Because in the case of the JWST, it was decided to have one image for everyone. In other cases, sometimes there's, like in Nature, one image published for the scientists, and then the press agencies decide to create their own image for the public. So these are things we want to be aware of and kind of decide upon in a systematic fashion rather than being at the whims of the press agencies or whomever. Okay, a fifth type of contribution that we're working on is how to structure the collaboration. That's one of the things I myself are particularly involved in. And one of the many ways of categorizing different types of collaborations is along this spectrum, where on the one side you might have what I like to call top-down collaborations, which can be very hierarchical, lots of committees who make all the decisions, which can be great if you just have very specific goals, like detecting the Higgs boson, but there's always a risk that it's not necessarily that great for individual members, for individual creativity, for freedom, for dissent, so we need to be quite careful and very top-down, paradigmatic top-down collaborations. And on the other end of the spectrum, you have very bottom-up groups of scientists. It's very loose, lots of room for dissent. People can do whatever they want, but then if you want to, this is very tricky. If you really need to coordinate, lots of people need to work together, lots of fund is needed to really achieve greatness. So I think our task here, or our ideal, our dream, is to try to make sure that the JWST is right in the middle, of course, in the sense that it's the best of both worlds and not the worst of both worlds. Now, how do we go about that? We're trying to work at many fronts simultaneously to try to achieve what I said on the previous slide. So let me just go through some of these things we're working on and many of the people in this room are working on. So one very important thing that kind of feeds in all the other work we're doing is trying to get a handle on, kind of a good grip on how communication flows within a collaboration, whether it's Atlas or the JWST. So we're trying to use what's called digital humanities tools, where we analyze mailing lists or minutes of recordings, or all the kind of digital data that's available, to get a sense of how information flows within the collaboration. And we can get nice graphs like this, detect which sub-communities there are, which teams there are, where the communication mainly goes via a few mediators or liaisons, or where there's more direct communication between all the communities, what these communities are. And then when we have that information, it feeds into much of all the other things we're doing, right? Like once we know how many teams there are, etc., we can start thinking about maybe the team sizes are too big or too small, or needs to be more communication between certain types of teams, etc., etc. But for all of that, we need this information. And this will then also feed into optimizing like our authorship policy, regular climate surveys, governance structure, etc. So this is kind of really step one to achieve all the other things we're trying to achieve and focus on. So here are some of the other ones. Let's focus on conduct, climate, and conflict resolution next. So this task force is, so one tricky thing is normally if you just work in one institute and there might be a conflict, then there's an HR department you might be able to turn to. But when you're working with a global organization where there's not just like a global HR department, you need to think about these things. So that's what we're doing. This task force has, for now, drafted a code of conduct, where the idea is not to just have a one-page kind of toothless list of cliches, but really have a code of conduct that's tailored to the needs of this specific collaboration, that gets updated regularly, and that's really created, and for instance, a town hall with the whole group, and not just, these people took initiative, but in the end, it's a code of conduct, which is supposed to be a code of conduct of us all. So that's what we have been working on, and we'll continue to work on. Then next, one thing which I think is quite unique, at least within the context of astrophysics, is a forecasting tournament led by Alex Markoc. And the idea there is that we kind of want to systematically, or like we want to keep track of what the members of the collaboration think are the predictions, the potential possible outcomes of the NGHT, and also what their likelihoods are. And you might ask, like, why do we care? Surely once we get the data, we kind of remember what we thought was going to happen in the past. That's often not how it goes. Mostly when I talk to particle physicists, they will tell me the Higgs boson, many of them will say it's kind of inevitable that we would detect the Higgs. When my colleagues interviewed people before Higgs Dependence Day 2012, we got a very different picture. So we don't want to rely on all our memories, but very systematically keep track of all these predictions and their likelihoods. So there are a few ways of doing that. One way I like is kind of setting up an online market system where all the members can kind of sell and buy hypothetical bets, like, oh, okay, I'll buy a bet from 1 to 3 odds that we're going to detect a photon ring. And then eventually you'll get a market equilibrium, which might change over time. And then you can keep track of what the collaboration as a whole thinks is going to happen and how likely it is. And this is not only interesting for us philosophers trying to understand science and hypotheses and how they develop and are evaluated, but it's also very important for the collaboration itself in real time. Right? There's always limited number of resources, money, time, people. So you really need to decide, well, how are you going to design your array, right, the back end, which frequencies are you going to observe at, etc. So then it's really good to know what you think are the most likely outcomes, how likely they are, and for each of those, what you need, what kind of array you need, right? And similarly, once you finally have results, it's good to know, for instance, for your Bayesian priors, but also for your results, how novel they are. And then it's good to know what you thought in the past and if there's something surprising that came out of it or not. So that's what we're doing here. This forecasting tournament is in progress. Okay. Then another quite important topic, consensus and dissent. It would be very naive to think that 400 or 300 people are always going to agree on literally everything. So this task force is thinking about, is a collaboration? Can a collaboration such as the NGHT be a democracy? What kind of democracy? To what extent? Are there forms of dissent? Like currently they're working on a typology, like delineating different forms of dissent. Which ones are those that are great, that you want to incentivize? How do you do this with a certain governance structure or otherwise? Are there types of dissent that are just disruptive and not beneficial? So that's what this task force is focusing on. And Vitaly and Peter and many others here are the people to talk to if you have any questions about these topics. Okay, yes, 5 minutes left. Another important topic, these topics are all related, is governance, right? You need some overall structure with such a big group of people. So what this task force is doing is very systematically analyzing kind of similar collaborations, their organizational structure, what are things that worked well, best practices, what are things that didn't work so well we need to avoid. And the idea here is not, so as of yesterday, there's kind of a report or an agenda-setting document based on the systematic analysis of all these case studies. And the point is not here that we come in and want to say, this is the one unique best way to organize a collaboration like ours, but more this document is like a list of all the things we need to consider when we as a group, for instance in the town hall, want to decide, okay, this is how we want to structure, how we want to organize ourselves. These are things which didn't work in other contexts. These are things that maybe do work in our context, etc. So the idea here is that systematically, the discussion can be structured, that systematically we know what to consider when we're deciding all together how to organize ourselves. Almost coming towards an end. One final topic that we're working on is authorship. Right, we're writing a paper with 300 people is quite different from traditional authorship, where you write it with 1, 2, or 3 people. So there are lots of challenges related to authorship in such big groups. Right, the different sub-communities involved. For some, authorship might be much more important than others, or mean something different. If you're a junior member and you write a paper for a very long time and then you're author number 271, it's not necessarily great for your job prospects. How to deal with dissenting opinions. Do you insist that you can only ever speak with one voice, or is dissensus to some extent allowed, and in what form? Also, who decides, when do you decide upon the author list? If it's straight at the beginning, determined who is first author, then maybe the rest of the group is not incentivized to contribute. Of course, if you decided at the end, this leads to other problems and biases. So these are lots of challenges to think about. And one of the things we try to emphasize is that there are many ways of assigning credit. It's not a zero-sum game. We try to advocate just try to assign credit in as many ways as possible to make as many members as happy as possible. So here are some of them, but I don't think I have time to go through them. But of course, for many of the communities involved, it seems like in the foreseeable future, authorship, especially first authorship, will remain the main currency. So what we've done is drafted a survey with the idea of sending this to all the group members and discussing all these possible ways in which we might have an authorship policy which makes as many of us as happy as possible. And with my JWST hat on, this is all I'm going to say. But if you want to know my personal thing of what I think would be best for this collaboration, come talk to me afterwards. So I think this is most of what I had to say. I tried to present you with a smorgasbord of all the kind of flavors, all the things we're doing. There are many people here in the room you can talk to if you want to continue this discussion. Or we also have our white paper, and we contribute to the key science goals document. And they're very a few shorter summaries of what we're doing and what we plan to do, etc., etc. So I would say thank you, Mary, very much for your attention, and we would love your feedback for this collaborative effort. Thank you.
Thanks, Niels. Yes, questions?
So going to the forecasting tournament, I heard you say something about placing bets. I am curious how this proceeds, and if a bet wins, like what are the rewards? Are we talking cookies? Are we talking, lay this out for me.
Yeah, no, like I said, so what I was describing there is what would be my favorite way, which in the end currently is not actually how we're proceeding. We are proceeding more in small focus groups, asking small groups of members what they would do. In other fields like ecology, etc., these are the methods which are typically used, especially like gigantic groups, and it's really more hypothetical. But like it's gamified. Like there's no, I mean, maybe you could add cookies. The point is not to create disruption by high stakes bets. No, these are hypothetical bets. Now, in some case, these bets between famous people are fun and interesting and help, but that was not the point here to make it right. It's more like, what would you do? Like it's more like a game. Which bets would you take to try and score the most points? So sorry if that's not what you hope for.
No, I'm just curious how it would improve your culture if you were like it was high stakes.
Yeah, so there's supposed to be no stakes whatsoever here. Yeah, for the reasons you're, I guess, alluding to.
Yeah, thanks for the great summary. I was curious if you've had any discussion of, in these other projects, of the rules kind of evolving with the project. So for instance, the nature of conflicts are very different at a project formulation phase versus when you're publishing the very first results versus later on when it's kind of eased into an equilibrium. And likewise, authorship policies probably change a lot over what makes most sense for, say, the first major result of a collaboration versus, routine papers that come later. Has this come up in how you're thinking of your policies, or does this, have other collaborations dealt with this kind of evolving structure?
Yes, we've talked about it, but not yet really come to an amazing solution. So in the case of authorship, right for now, we've written mostly white papers, so that's, I guess, different from the eventual papers. And there, I think one thing we're trying to advocate is to have, there are often collaboration papers and other categories with various names. I would advocate that we should have more of those, right, smaller groups, but this will depend indeed on the phase. When it comes to governance, we're talking a lot about, it seems to be the more democratic, the better, the more problems are being prevented in the first place. So that's something, so some of the, where is it? Yeah, so one thing we think would be very good to have like a science council where all the stakeholders, and of course who the stakeholders are is an interesting discussion, should be represented, and I think it would be good if those are elected positions. So one thing that's in the agenda setting document is all about which of these positions should be elected, and that might differ in different phases. Ideally, you might connect it with phases of the project, but of course, some positions it doesn't make sense because of contractual obligations to elect them. So I guess we're focusing more on having a setup and a structure that events, I mean, we're also talking about conflict resolution, but having a setup that kind of prevents any conflicts as much as possible by having mechanisms in place or a scientific council, etc. People, their voices are heard before things escalate. But yeah, these are ongoing discussions, and right now I don't feel like I have a one-size-fits-all solution. Yes, these are ongoing, and any people who have input on this, we'd be very interested to hear. It's very difficult to give a general solution because it's usually the details that matter. But yes, we're definitely talking about this. To be continued.
That was a very nice presentation. The one thing I wanted to ask about was verification and validation. So for the Event Horizon Telescope, it was very critical for us to get the data out to the public. And then there were a number of independent groups that imaged the data using algorithms that were different from the ones that we used. And that was extremely important for acceptance. Mm-hmm. As we move to the NGHT, we'll be looking at videos and different data products and different fundamental deliverables. So where does that play a role in the representation of the collaboration to the general public and to the scientific community?
Yeah, so I think I'm going to defer to the experts on this, who are kind of sitting over there, who are working exactly on this, and there's a very nuanced answers to this, so I'm not going to try to summarize their work and not do it correctly, but I should just chat with them. Hope that's okay. But yes, very good questions.
Let's take one more question.
Sorry to monopolize. This is a great talk.
Thank you.
And many of your topics kept pinging me on one concept, academic freedom, right? Each member, by signing on to a collaboration like this, is giving up some of their, academic freedom because they're going to follow rules that are designed by the whole group. It looks like a negotiation of some sort, but except it's not. It's not individually being negotiated, but collectively one is deciding. And the whole thing is very mysterious to me and also makes me feel a little uncomfortable because, as an academic, I should be able to say what I want. And for instance, Shep's question or Michael's question, right? If there is a result here that, 95% of the group says, yeah, this is it, I feel like I should be able to be the 5% that says, no, I actually think that's the correct answer. But in some sense, one is giving up that freedom. How should I view this?
Yes, so let me say two things. One, it's basically indeed a social contract. And what I definitely personally, but also some of the members here really want to stimulate, basically I'm repeating what I said to Michael, somebody, whatever you want to call it, where kind of everyone not necessarily directly gets a say, but everyone is represented in one way or another. So to mitigate some of the problems you mentioned. But yeah, in terms of very concretely, if it's about the content and the disagreement of opinions, we're toying with a few ideas which we'll throw into the authorship survey, right? So one of our members, Haisen Dang, is talking about, she compares authorship to the US Supreme Court, where often if some of the judges disagree, nonetheless there will be a majority ruling which is binding, but they will produce a minority report, which will be published, and people can see this. So we're talking about whether that in some cases, but it's very hard to decide in which cases, should we do it as a collaboration without us risking journalists misinterpreting it, right? Yes, so these are things we're toying with. Some of us think it's going to work, some are not, but we don't want to decide it for the rest of the collaboration. So yes, there are some of these models which we'll mention in the authorship survey, and we'll see what people think, and if they think there's some cases where this is a good idea, some cases not, or maybe you think, well, it should be like as an appendix, or maybe it should be discussion session. You can think, should people sign their names to these things, or should it be anonymous? We're considering all of this. We're not going to decide it for the rest of you, but we'll give you a list of options, and we're curious to see what the majority thinks.
Thank you so much for this really nice talk. So I'm just following up on this. Might it make sense to just have a section that says process of reaching consensus, like how the consensus was reached on the results published in a particular paper, and there kind of outline the agreements and the disagreements. Is that something?
I
Because,
like
I mean,
that
I
idea,
think-
but I
yeah.
don't want to speak for the rest. But yes, that sounds great to me. I don't know if any of the dissent task force people have different ideas, but yes, I love that.
That would be quite interesting, I think, just for all of us scientists who are also interested in how science works, but also for the historians and philosophers of science as a record of how the project and the results unfolded.
Yeah, and then you have to ask the question, do we want that to be part of the paper, more like a Nature commentary or one of these commentaries, of kind of publish them in tandem? I don't know what the right option is, probably depending on the case, one works better than the other. But yeah, I love that idea. I'll throw it in and hope other members of the collaboration that things in some contexts we should go for that. Yeah, love it.
Okay, thank you, Niels. And thank you to all the speakers of the first session.
My name is Evita Verheijden. I'm a theoretical physicist and a postdoctoral fellow at the Black Hole Initiative. This will be the second session of today, and we're very happy to have Phil Hopkins, who's a faculty in the theoretical astrophysics group at Caltech. And I think his presentation is being pulled up. He'll be speaking about the black hole galaxy connection across vast scales of time and space. Please.
All right, thank you. Pleasure to be here. I'm, as I said, a professor at Caltech, and I do a lot of numerical simulations of things like galaxies, stars, supermassive black holes, and all their interactions. So this is movie time. I'll use the excuse that I'm a simulator to show lots of beautiful animations from the numerical simulations. And hi to several of you in the audience that I remember from graduate school when I was here. And I do just, of course, want to say all of these simulations are worked by a very large number of people that I don't have time in this talk to acknowledge. But I want to give folks here, since this is a broad audience, a kind of idea of what this black hole galaxy connection is and why it's become such a major subject of work in one of the biggest fields of astrophysics, sort of extragalactic astrophysics. There's hundreds of astronomers working on these problems. So we know that supermassive black holes exist, and I don't have to tell this audience about that. We, of course, see beautiful cases like Sag A star in the center of our own galaxy, which I apologize, I had to convert this talk to PowerPoint, so a couple of the movies seem like they're being grumpy, but at least some of them clearly work. So we see stars orbiting around the center of Sagittarius A star, but we also see these incredibly luminous quasars and bright galaxies where there's accretion onto a supermassive black hole happening at incredibly high rates. These are the most energetic sustained sources in the universe, basically, powered by accretion. And of course, we've got beautiful imaging. I don't need to tell folks here about things like EHT confirming these black holes on small scales. But one of the challenges is the tremendous dynamic range of scales involved. So on the left, we have a famous galaxy where this supermassive black hole is accreting and launching a relativistic jet of material out. And this is going into the circumgalactic medium to scales of megaparsec, or something like 10 to the 24 centimeters away from the galaxy, and influencing the medium around there. And yet the event horizon of this black hole, where most of that energy is actually being generated and liberated before material crosses the event horizon, is at scales of order an astronomical unit, of order 10 to the 13 centimeters. So you've got 10 to the 11 factor of scales that are strongly coupled to one another, right? And that's just fundamentally intractable to brute force put on a computer and do all of that at once, basically. Nonetheless, we try to make progress, and there's plenty of reasons that we're interested in this from the sort of extragalactic astrophysics point of view. They're probes of very high energy astrophysics. Basically, other than direct matter, dark matter annihilation, black hole accretion is nature's most efficient engine for converting mass into energy, and it's the most efficient engine that nature does frequently, basically, because antimatter is rare, basically. So that's why they're so energetic. Of course, they allow us to test our theories of gravity. They allow us to probe the new burgeoning field of multi-messenger astrophysics and get qualitatively new constraints. And all of this is not what I'm going to talk about. But they can also tell us a lot about galaxy and star formation and are critical for it. And this really came to the forefront, as Ramesh alluded to earlier, in the sort of late 90s, early aughts, with the discovery of fairly tight correlations between supermassive black hole properties and galaxy properties. So we've known since the discovery of quasars that you could, since shortly after the discovery of quasars, that you could power these luminous luminous objects with supermassive black holes at galaxy centers. But we didn't appreciate that there was this tight connection between the properties of galaxies and the properties of the black holes in their center. And this is most famously encapsulated in relations like the M-sigma relation or the black hole host galaxy mass relation. These are just correlations between black hole mass and various properties of its host galaxy, where they obey some tight correlation. So in mass, the black hole is something like a part in a few hundred of the mass of the stars in the central part of the galaxy, with a surprisingly small scatter. Now, that scatter has crept up as we've discovered more oddballs and outliers and things like that, but it's still, within a factor of a few, you can predict a black hole's mass based on its galaxy mass, or vice versa. And that's, pretty non-trivial given this vast range of scales I just described. The galaxy stars are primarily residing on scales of order kiloparsecs, hundreds of thousands of light years, or tens to hundreds of thousands of light years, and yet the black hole is on scales of AU. In terms of mass, the mass scale is maybe a little more similar, but it's a factor of 1,000. The gravity from the black hole only matters to the dynamics of the galaxy inside of a couple light years around the black hole. That's the only place that stars appreciably feel the mass of the black hole. But of course, what I'm going to come to is this phenomenon of feedback. And this is the idea that what is not very different are the momentum and energy scales of the systems. Because black holes are so good at converting mass into energy, that small amount of mass is able to create an amount of energy, or liberate an amount of energy, that is comparable to the gravitational energy binding all of the normal matter into the galaxy, basically. In fact, it can quite easily exceed that by a factor of 10 to 100 or so. And so in energy scale or momentum scale, things that maybe a particle physicist would like to talk about, these are actually very comparable objects. Suspiciously comparable, and I'll argue that's not an accident in our current way of thinking, because they're linked through that transfer of energy and momentum between these two types of systems. But modeling this is really hard because, as I said, it's multi-scale. It's also multi-physics. So a lot of these problems in astrophysics on these scales, the challenge is not new physics. It's not what we just heard about probing quantum gravity. Some physicists would say this is all solved. These are all things that, we knew how to write down some of the equations for somewhere between the 18 and mid-1900s, basically. But of course, you can't just say, I know the fundamental equations for an atom, therefore fluid dynamics is solved, right? And likewise, we know the fundamental equations on sort of large non-relativistic scales for most of these things, but they're incredibly complex, nonlinear, chaotic, multi-physics processes operating over a huge dynamic range of scales and parameter space. That most of these parameters, what I love about astrophysics is these are wildly different from anything you could ever probe in a laboratory in terms of the strength of gravity, in terms of the how low density the material is, in terms of the regimes of the sort of atomic physics that are occurring, et cetera. And this leaves open some big questions that people in my field and related fields are still grappling with. So from the astrophysics side, we're still wondering, where do these supermassive black holes actually come from? What are the seeds, you might say, that grew into these things? How do they grow? We think we have converged somewhat as a field that they grow primarily via accreting gas from their cosmic environments, with some contribution. Maybe some of them grow more by merging with other black holes, although I think the consensus is most of them probably grow primarily by eating gas. But where did that gas come from, and how did it get from enormously large scales like the cosmic web down into the black hole? And then what do they do to their surroundings through these feedback channels I described? To do that, we need to look at their interactions with their galactic environments. So just a reminder for those who aren't in these fields, what's a galaxy? Well, here's an image of a galaxy, and what you're seeing here is a very famous galaxy called M82, or sometimes the Cigar Galaxy, that's been studied to death because it's a great example of feedback and incredible action. And it looks really boring if you take an optical image of it. It's just, okay, it's a disky galaxy, but it's viewed kind of edge-on, so it just looks like a flattened thing with some dust lanes. But you view it in other wavelengths, you view what the gas is emitting, and now you can see why this is a famous galaxy. It's got these huge explosive outflows of material coming out from the galaxy, going out to hundreds of thousands of light years from the galaxy center. And these are viewed in basically every wavelength we've been able to trace gas and dust emission. So this is a composite of things like the hydrogen alpha line, X-ray emission from hot gas, dust emission from cool, warm gas, et cetera. So the visible light is coming from there. The X-rays are coming from gas at millions of Kelvin. The infrared, dust and soot, the stuff that planets and us are made out of, etc. And then, of course, there's the things that we can't see directly but have to infer indirectly that go to even larger scales, the dark matter that encompasses these giant dark matter halos full of much more tenuous gas held in by the gravitational potential of the dark matter, going out to something like 100 times larger scale spatially, full of these substructures. And of course, again, we have lots of techniques for decades that have mapped this out indirectly through its gravitational influence. So how do we model this? Well, for somebody like me, the idea is what's the recipe for making a black hole and understanding it? Well, I take the ingredients, which are the cosmological recipe that we heard some mention of, things like dark matter, dark energy, and normal matter, and we put those into a computer. Now, you might say, well, we don't know what the dark matter and the dark energy are. Fine. I know pretty well what the dark matter does, though. To leading order, the dark matter interacts via gravity, because that's how we detect it, and it doesn't interact via electromagnetism. It's dark. All right, that gives me something to start with. I'll model something that interacts via gravity and has basically no other force interactions with a standard model. There's a whole subfield, and a lot of my work is on what happens if you make different particle dark matter models. What does that do through various indirect channels to galaxies? I'm not going to talk about any of that, but for now, we'll just treat it relatively simply. Dark energy, at least phenomenologically, we know even less about, but seems to act only on extremely large scales. So to 0th order, it's mainly important for getting the expansion and growth history of the universe right, but doesn't have much of an effect on small scales, that relatively small scales, only, 1 million light years or smaller, basically. And then, of course, these things that, again, we sort of know the equations for, but are incredibly complicated to model on large scales. So then you have your ingredients and your initial conditions. So for somebody like me, the initial conditions, I don't care what happened in inflation. I know roughly statistically what the universe looked like a few 100,000 years after inflation, when we have the cosmic microwave background relic radiation that maps out the statistical properties of the density fluctuations in the universe at that early time. This here from the Planck telescope. So I can take that, add some simple equations. On the largest scales of the universe, to 1st order, gravity is the dominant force because everything else cancels itself out. And so gravity is easy. It's mostly non-relativistic on these scales. No horrible GR equations needed here. Force is equal to GMM over R squared. You just need to solve that, trillions of times over and over to integrate the trajectories of billions upon billions of elements. But, computers are really good at solving a simple equation a ton of times, right? So this is why we parallelize this on supercomputers and turn the crank, and boom, you get your simulation of cosmological structure formation. Sorry, I skipped the actual movie there. It doesn't want to play. But basically what happens is that gravity starts pulling together the regions of the universe that are slightly more dense. Here we go. Now it should work. What initially looks very homogeneous has tiny fluctuations. If there's a little more matter over here, it pulls more stuff towards it. That means that there's even more of a gravitational imbalance over here versus over here. More stuff gets pulled towards it, and this process runs away unstably until these structures collapse into what we call dark matter halos. These are structures that have coherently collapsed under their own gravity. They've broken apart from the Hubble flow. Notice this whole thing isn't expanding. In this movie, I've sort of factored out the overall expansion of the universe, because otherwise the movie isn't easy to watch, because it just goes from a point to kind of expanding past the board very quickly. And when you're done with that, you get this sort of cosmic web, this network of collapsed gravitational structures, these dark matter halos. And if you ask about the distribution of matter on large scales, if you make, say, a mock observational map, these are some observer coordinates where we would put galaxies in a survey of galaxies. 2 of these wedges are fake, just putting a galaxy in each of these dark matter objects, and 2 of these are real. And if you tell me you can tell the difference of which is which by eye, you're lying, because no test we've been able to construct essentially can tell the difference between these. This is the success of essentially the modern cosmological model, is that to most or all of our statistical tests, these are effectively indistinguishable from each other. So that's success on large scales. And you might imagine we just need to paint some galaxies on there. So how do we paint galaxies on? Well, we need to add more than just gravity. We need to add things like fluid dynamics and chemistry, because galaxies are composed of gas and stars. Gas can do things, for example, like radiate energy. So gas, atoms that fall into a galaxy can do things that are different from the dark matter. So our cartoon model for how a galaxy forms is that gas gets pulled in by the gravitational potential of the dark matter, because most of the mass in the universe is in the form of dark matter. It is pulled in supersonically under gravitational forces, so it slams into itself supersonically, which means you get a big shock. That shock heats the gas up to some very high temperature. So now you've got a ball of shock-heated gas. But that gas can radiate, because you've got things like ionized hydrogen. The electrons and protons can recombine, emit a photon. And the universe is so tenuous on large scales, the overwhelming majority of those photons are going to freely travel forever. And they're never going to intercept anything, except if we're lucky, a telescope of ours. And that energy is essentially lost to the heat bath of the universe, basically. And so the gas can cool down and lose energy. And what is it? If you're sitting at the top of a potential well, held up by this energy and pressure of hot thermal gas, and that gas cools down, now all of a sudden there's less pressure. So what happens? Gravity wins and you fall down. You fall down the potential well, which means you fall into the center of this. But if you have any tiny amount of angular momentum, we all know what happens if something is spinning and it contracts, it speeds up in its spinning, right? This is where you, in Physics 101, do the figure skater demo or something like that. And so it spins up faster and faster until eventually it's rotating fast enough that the centrifugal force balances gravity, and it stops collapsing, and boom, galaxy solved. And I can iterate this process further within a galaxy, within the interstellar medium of the galaxy. I can say that there's dense clumps of gas within the galaxy that collapse and shock heat, and then they collapse and they form clumps, which collapse and form stars. And around those stars, gas clumps collapse and contract and form planets all the way down to the small scales. And this is just another simulation flying through that interstellar medium to the sites of star and planet formation. And so we might imagine an ambitious program to simulate all of this, not necessarily in one shot, given the tremendous dynamic range of scales, but we could go all the way down to stars, planets, and even black holes, scales of, they're roughly the same scale as solar systems, after all, these supermassive black holes, in pieces. We could take, say, our big cosmological simulation and zoom in on a patch of it, and do that at higher resolution and more physics fidelity, and then zoom in on a patch of that, and zoom in on a patch, and zoom in on a patch, and zoom in on a patch. And if gravity were the only dominant force in the universe, and cooling, this would work great, because everything would be top-down in terms of how it forms. And we can make some progress from this picture, but I'll return to that if in a moment. So we can ask from this things like, how do black holes get their gas? I was just showing this slide yesterday to Ramesh and others, and Priya, and saying, there have been many conferences on this topic with often different meanings, because people in the community, often when they say this, they might not mean how does gas get all the way into the event horizon, but how does gas cross X range of scales as it flows from the cosmic web ultimately into supermassive black holes. But again, there's this tremendous range of scales from sort of the intergalactic medium, the cosmic web, all the way down to below here into the black hole. But people are beginning to get a better and better understanding. So on very large scales, you have your cosmological simulations that do things like what I just described, where gas gets pulled via gravity through the cosmic web into these dark matter structures around galaxies. Once gas is inside of galaxies, there's been a lot of work to show that you have things like, sorry, the animation here is not playing. You have things like collisions between galaxies, or things like spiral arms and bars, these beautiful spiral arm structures we see in galaxies. Those are non-axisymmetric structures, which means that they break angular momentum conservation. There's some torque that arises whenever you have a non-axisymmetric potential, which means that you can remove angular momentum from the gas. Its centrifugal force isn't able to hold itself up at that same radius anymore, so it can spiral in further and further. And this can transport gas into the centers of galaxies. And that process can sort of iterate on smaller and smaller scales. And you can get structures like that all the way down to sort of radii around a light year or so, where the potential of the black hole starts to really dominate. It becomes this very Keplerian or Newtonian potential until you get all the way to the GR scales, where we don't have as good an intuition exactly what's happening, to be honest, because you're sort of crossing between a lot of physics scales. And then you form these accretion disks of swirling material around the black hole that can sort of exert some effective viscosity or stresses on the gas to try and remove its angular momentum and transport it the rest of the way. And there's been lots of work on this. I'm going to show a movie from some recent work that I was advertising yesterday. This is all more technical about some of the physics that's included, where we're trying to follow this in numerical simulations. So this is just a static instant in time where we're falling in from a simulation that started on 100 megaparsec scales, scales of order of the cosmic web, all the way down through one of these high redshift, early universe, massive, turbulent, clumpy, messy galaxies, and watching gas get torn apart and swirl around. So basically a giant cloud complex that was forming stars at a tremendous rate gets knocked by the collision of different galaxies towards the center of this galaxy, passes by a 10 million solar mass supermassive black hole, and that black hole tears off a big shred of this through its incredibly strong tidal forces. That big shred gets wrapped around the center of the black hole in its own potential and forms this accretion disk that then is able to move matter inwards further and further towards the black hole. And the subject of our discussion yesterday was that simulations are getting better and better at bridging this range of scales. This still doesn't include GR and the physics that are really important right near the horizon, but we're finally getting to the point where we can start connecting these simulations from galaxy scales to those kinds of numerical simulations without having to do necessarily 25 different stages of simulation in between to bridge the steps. Sorry, I'll skip this. This was part of the, again, I think in my conversion, this got skipped when it shouldn't have, but this is just some illustrations of these filaments of material. Each of these little dots is a star, so there's still star formation happening and structuring the gas, and these lines are like zooming from large to smaller scales around the black hole, the magnetic field lines, which get tangled up and twisted around the black hole and do really important things for structuring these accretion flows onto the black holes. And you could give many, many talks just about this image, basically, and what that magnetic field structure means for how black holes grow and accrete. So we might say, okay, great, we're done. We've gone from top down, and at least if I patch that onto a GRMHD simulation that other people here work on, they could follow that flow all the way into the horizon. Problem solved. Great, let's go home. Of course, it's not so simple. So far, everything has been top down. And if all you do is sort of say, everything is top down, gravity is the dominant force, there's some chemistry processes that allow for cooling and dissipation of energy, and some rule that eventually sufficiently dense gas will turn into stars, it turns out it's a complete disaster. And the universe looks nothing like what we observe, if those are your rules, on smaller scales. And smaller here means less than 100,000 light years or so, basically. So this is one particularly famous example. This is what we call the galaxy mass function. It's just the number of galaxies as a function of their total number or mass of stars contained within that galaxy. The white line is what's observed. The blue line is what this simple model generically predicts. And essentially the blue line is that the prediction of the blue line is every galaxy's dark matter drags in about a 5-to-1, a 1-to-5 ratio of normal matter to dark matter. Along with it, that's just the universal average ratio, and converts 100% of that into stars, basically. But that's nothing like what we see. There's factors of hundreds or thousands gap between these predictions here. Worse yet, they're not actually stars. They're all brown dwarfs. They're all about 1% the size of the sun. There's also no such thing as rocky planets in this universe. It turns out, under these assumptions, everything is a gas giant. Basically, everything turns into objects in a sort of preferred mass range between about, 10 to 100 times the mass of Jupiter, basically, for just atomic physics reasons. That's sort of the only mass scale you can select out. And there's a bunch of other things, if I wanted to go into more detail, that are messed up here too. And this has manifested in many famous crises or problems. Whether you call it a problem or a tension or a crisis may depend on whether you're trying to get your paper into Nature or not. But the most well-known, even to people outside of the field, is sometimes called the missing satellites problem. So this is the problem that if I take that naive prediction, I predict a swarm of thousands of luminous satellite galaxies orbiting the Milky Way. And that is simply not seen. We see dozens of incredibly faint things orbiting around the Milky Way. We only see a couple luminous galaxies orbiting the Milky Way, literally two. The Small and Large Magellanic Cloud are the only two galaxies you can see by eye, and there should be hundreds that size in my simple model, for example. So why is our galaxy so alone? Why is the universe so bad at making stars? And this all comes back to what did we miss physics-wise? And this is where these feedback processes are so important. So I'll mention feedback from stars and from black holes. So, of course, stars themselves can't be neglected because you can't just say mass goes into a star and then it's done, because stars do stuff. By definition, stars shine, right? We wouldn't have a field of astronomy if stars didn't shine. We also wouldn't have life on Earth, presumably, if stars didn't shine. And that radiation can do stuff. It can heat up gas. It can blow gas away from those stars. Stars also blow winds. Even our sun, which is very dinky by the standards of these kinds of processes, is blowing a powerful solar wind. This is real data for our sun's solar wind being blown off the surface of the sun. And more dramatically, of course, this is now an artist's impression, stars can explode, right? They can reach the end of their life in various ways and explode as supernovae. And when you add up, we know this is happening. We see it happening all the time in nature. We see it happening on the fly, stars exploding. There's that same M82 galaxy with a supernova that went off 10 years ago in it, where the supernova is bright enough to see relative to the whole galaxy by naked eye, basically. That bright dot is not added to guide your eye. That's the supernova light. And so stars do all of this, and that energy cannot be neglected. And black holes really take this process to 11, basically, because they're so good at turning mass into energy again. So this black hole of a few million times the mass of the sun in the center of our galaxy, at some point during its life, could have been one of these ultraluminous objects, these quasars. And in fact, we think at some point in the early universe, it probably was, when it was growing most of its mass, where the luminosity could be 1,000 trillion times the luminosity of the sun, basically, coming out of a region the size of the solar system, basically. These things can outshine their entire galaxy by a factor of 1,000. Right? The brightness of the quasar, that's one of the reasons that for the bright ones, it's really hard still to know what kinds of galaxies they live in, because they outshine it by so much that just the sort of artifacts, from your imaging are overwhelming the light from the host galaxies. And again, we come back to, we have these giant relativistic radio jets that are impacting the medium around them tremendously. You've got material moving at nearly the speed of light, impacting the medium on large scales. So what does that do? Well, here's just a toy example of a little cloud of gas that has that's going to form some stars and black holes. And on the left, the movie is going to show what happens if those were just passive, if they just accreted but did nothing. And on the right, it's going to include our best guess of what comes out when you swallow stuff in terms of radiation and jets and winds and things like that. And you'll see the one on the left just turns into more and more stars. The little white dots are the stars. And the one on the right, the second it starts turning anything into stars or black holes, those start blowing bubbles and cavities within this system, basically. And they destroy the entire region. In this case, it's mostly stars doing the work. But I could show a similar movie of the center of a galaxy for the black holes. They end up blowing up this whole region after it turns just a fraction of a % of its mass into these compact objects, because those liberate so much energy back out into the medium, basically. And so you get things like these giant galactic winds being launched out. So at the center of this M82 galaxy, you've got something like, in the last dynamical time or orbital time of the material around this galaxy center at this radius, which is something like 10 million years, there have been something like 10 million supernovae. Or one decent burp from the supermassive black hole in the galaxy, which will give you about the same energy as 10 million supernovae, is enough to launch all of this material out from the galaxy at thousands of kilometers a second into the intergalactic medium, basically. And so we return to this picture, and the problem is that these small scales strongly couple back to the large scales. So, tongue-in-cheek, nature hates theorists. This is why this problem is so hard. But so interesting, right? Because all of these scales are actually strongly coupled. And I shouldn't even just draw the arrow coupling this to this. Really, all of these scales can crosstalk via these mechanisms very rapidly. So, just to wrap up the last couple slides, I just want to show a couple pictures of a couple movies of sort of how we think this comes together in the life cycle of a galaxy once you include these processes. So this is an example of an animation of what we think the history of, say, a Milky Way-like galaxy would have been, where in the early universe, I apologize, it's not animating on the left, but if you look at the right, which shows the gas that would form the galaxy, it has this sort of early, turbulent, messy phase where stuff's coming in fast, stuff's blowing up fast, though, too, because of these feedback processes from stars and black holes, launching material back out as soon as it's coming back in, basically. And it's not until quite late in the history of the universe, this is the cosmological redshift factor, so until about redshift 0.7 in this particular case, which is about half the age of the universe, when the universe got to about 7 or 8 billion years old, is when this thing finally starts to really calm down. It's starting to calm down around now when the universe is like 5 billion years old. It has one last big burp because there's a galactic collision that feeds the black hole and starburst in the center and causes one last big blowout of material. And finally, only at late times does it return to sort of our cartoon picture of gas shock heating into this hot halo of gas that gently cools, conserving angular momentum, and builds up this nice big spinning disk of material that returns to the cartoon that I showed you earlier that was proposed in the 60s. And it sort of works for the last couple billion years of the universe's life, but it's a very incomplete description. I didn't push the button. That's why you didn't see the other image. And lots of people have worked on showing that you need stars and black holes, with a general consensus picture is that for the small galaxies, what we call dwarf galaxies, the stars are the primary energy source, although they absolutely have AGN and black holes, and we're still arguing about how important the black holes are down here. But pretty much everyone in the community agrees that no amount of this energy from stars alone, there simply aren't enough stars to regulate the most massive galaxies, which are also the galaxies that host the most massive black holes. So if you want to explain why M87 looks like M87, you need the energy from these supermassive black holes. And basically, they blow themselves up, or their galaxies up when they get too big because they release such an enormous amount of energy that they cannot grow any bigger. And this is sort of an old movie by Tiziana Di Matteo and Volker Springel showing this process in action in a simulation. And that's basically everything I wanted to say. These were the ambitious slides if I had the time just to show some extra pretty movies. But I'm going to skip them. The point of this all is once you include all of this, you get a universe that's much more similar to what's observed. It's not that this field is solved by any stretch. We don't understand a lot of these physics and couplings in detail, but it's at least plausible. This is the computer model, including all of these processes where we're flying through a galaxy, but on large scales, you didn't see these hundreds or thousands of small luminous galaxies because they were all able to be efficiently blown up after they formed a small number of stars or black holes and suppress future generations of star formation in those galaxies. And so but also challenging field. And that's everything. Thanks.
Wonderful. Thank you so much, especially for the beautiful movies. I think we have time for one quick question. I'm really going to cut it off right there. Yeah, Andy.
Thank you for the beautiful talk. This may be an impossible question, but I'm wondering if you could go back to that beautiful thing with the squares where you kept blowing up different pictures of the universe.
Oh, yeah.
And could you say in one sentence for each square what we understand from simulation and what we theory and simulation and what we understand from data?
Yes. I mean,
and what?
You know,
yeah, just
the
really briefly. You said it all, but it was scattered throughout. I'm having trouble.
Yes. I mean, I was trying to cover too much, as I always do, especially for this audience, where I'm trying to give an overview of the field. Is this the slide you were referring to? Yeah. So, I mean, I could honestly give a whole talk easily about each of these squares. You know, I think on the very largest scales, which is what's shown up here, where you're talking about the cosmic web and the distribution of matter on very large scales, that's actually the best understood scale because it is to first order just gravity that's dominating it once you include that there is some right ratio of dark matter. And that's the thing we can model with the greatest success. As you go to sort of galaxy groups, that's where you start worrying about especially the effects of black holes burping out and changing the distribution of matter on large scales. And there's a lot of work on next generation surveys of diffuse circumgalactic matter, things through techniques like the Sanyaev-Zeldovich effect, through absorption line spectroscopy to bright background sources and things like that. This is incredibly diffuse gas in these big groups that we want to probe its detailed properties because they'll tell us, is that gas primordial, for example? Does it have a primordial composition of hydrogen and helium that indicates it's coming in for the first time? Or is it enriched in heavy elements that would tell us that it's been through a cycle in the galaxy and gotten launched back out, right? And a lot of it's been observationally driven on those scales. On the galaxy scale, I think, you know, this has been led for decades by the observations. It wasn't till 10 years ago that simulators started making simulations that actually looked at all like a real galaxy, basically. And we've been playing catch-up for certainly most of my career. I think we're just getting into where the simulations are starting to make some real predictions instead of just trying to explain what's already been observed, but it's always a back and forth of those two. And I think the same thing is true on these smaller scales. Again, I don't want to take too much time, but I think on the interstellar medium and the scales of sort of individual stars or the regions right around black holes, we're mostly being driven by observations until you get really near the black hole horizon, where I think it becomes theory-driven again, because until very recently it's been so hard to observe and test things like strong gravity regimes, that kind of thing.
Great. Let's thank Phil again.
Thank you all.
For our next speaker, we're very happy to have Adam Levine. He's a postdoc at MIT, and he'll talk about cryptographic censorship.
Great. Thanks. Thanks for the invitation to come speak at this really awesome conference. It's a pleasure to be here. So I'm going to be talking today about some work that came out earlier this year with Netta Engelhardt, who's a professor at MIT and here at BHI, Osman Folkestad, who is a graduate student at MIT and is graduating today, so I actually don't think he's here. Evita, who just introduced me, and Lisa Yang, who's also in the audience, graduate student at MIT. And I just wanted to highlight that it was a real pleasure to work with these young people, young scientists. They're super bright. They taught me a ton about quantum cryptography that I didn't know and really carried us in this project in a lot of ways. Okay. So I'm going to start with the black hole singularity. It's sort of one of the big open questions, I would say, in my field is how do we think about the black hole singularity? What happens with this black hole singularity? And singularities, they are pretty generic in the context of black holes and in general relativity more generally. But even though they're generic, we know very little about them. We don't know what happens to space-time when you approach the singularity. We don't know really, we don't have a general characterization of when and where they can form. Sort of the second question that I'm going to talk about today, which is an old question. It's a question of whether singularities can form even in the absence of a black hole horizon. So this is really a question about the predictive power of general relativity in the sense that it is dealing with whether or not, given some smooth initial data, that this can evolve into a singularity, something that can't really be described within the low energy theory, and in a way that's visible to people who are sitting far away from all the action. They're sitting out at asymptotic infinity. This question goes back to Roger Penrose in the late 60s. It's been around for a long time. It goes under the name of the weak cosmic censorship conjecture. Penrose conjectured that this can't happen, much to the chagrin of experimentalists, because this would be great if we could have some access to physics that we don't understand in the universe. But something that the experimentalists might like is that actually the weak cosmic censorship conjecture appears to be false. At this point, we actually have a fair number of counterexamples to this conjecture. In higher dimensional black holes, there's this famous Gregory-Laflamme instability, which is related to when black strings, their horizons can pinch off and fragment into regular black holes. And right at the moment of pinching, much like a water droplet breaking, there's a region of high curvature that is visible from infinity and can't be described within general relativity. Perhaps in my field, a more famous example even is the example of an evaporating black hole. When you have quantum fields in a black hole spacetime, the black hole can evaporate. And at the end point of evaporation, there's a moment of very high curvature that, again, we can't really describe, but it is visible from infinity. And then more recently, there are some results due to various authors, mostly including Horowitz and Santos and their collaborators, on asymptotically ADS4 black holes and flat space black holes involving various matter profiles. These results are mostly, I would say less is known about these things, and they're mostly numerical. There's mostly numerical evidence for them at this point. But these seem to be yet one more counterexample. I just want to point out that these first two have something in common, which is that, as I maybe alluded to, the singularity, this moment of high curvature, is really only visible for a brief instant. It really is like a soap bubble snapping. And so maybe we say, well, in fluid dynamics, we're not that bothered by this type of effect. Why should we be bothered by it in general relativity? Maybe we just need to live with things like this. And it seems like we do. So we say, all right, so cosmic censorship is wrong. We just need to live with singularities. They can appear. That's great. Maybe we should look for them experimentally. But that's a bit too quick. We need something like weak cosmic censorship for the consistency of black holes. Because if we don't have an argument for why naked singularities can't be as typical as, say, a black hole horizon, that puts in jeopardy a lot of results that we have a ton of evidence for at this point. In particular, there's a deep connection between black hole horizons and quantum chaos, which I think will be discussed later this week by Julian Sonner. And the horizon, the fact that there's a horizon in most black hole states is very important for this connection. Probably even more famously, there's this Bekenstein-Hawking entropy formula for black holes, which says that the area of their horizon has an interpretation in terms of entropy. But if naked singularities are as typical as horizon geometries with a horizon, this interpretation falls under jeopardy. Okay, so the original conjecture is wrong, but we probably need something. So what do we need? We want a new version of this conjecture. So I'm going to focus on two aspects that you might like to have if you're going to formulate a new version of this conjecture. One would be that you'd like a general characterization, some kind of diagnostic of when you expect horizons to be present in your geometry. This is sort of the first part that I'll talk about, and it's the part where ideas from quantum cryptography are going to enter the game, and we call it cryptographic censorship. Or in other words, too much randomness leads to a horizon. And I'll explain what that means. And then you might also like to have a classification of singularities, because clearly some singularities are allowed to be visible from asymptotic infinity. So we need to decide which ones are the ones that we expect to be cloaked behind horizons and which ones are the ones that can be visible. And for this, I mentioned earlier that there's sort of the singularities of the Gregory-Laflamme instability and the evaporating black hole. They're only visible for an instant. So perhaps you want to formalize a size of singularities. So the challenge is to make that a different variant notion in general relativity. Okay, so these are sort of the two things I'm going to talk about. When you're trying to come up with a diagnostic of when horizons are present in the geometry, it was useful for us to go to this framework of ADS-CFT, of holography. Something like this was mentioned in Mina's talk. But this is really sort of the canonical version where you have gravity in asymptotically ADS spacetimes. In ADS spacetime, the asymptotic infinity is a time-like boundary. Call it scry. And the statement from Maldacena in the late 90s is that the dynamics, the gravitational dynamics in this ADS box is described by a standard quantum system on the boundary. It has a large number of degrees of freedom. And something I wanted to point out, so black holes in ADS This is an example of a single-sided black hole in ADS. It's the Penrose diagram. This is the center of the space-time, and there's some horizon shielding off the center from the boundary. But there's a region in the space-time which observers can start near the boundary. They can go in, explore the space-time, and come back out. This region I labeled by CW. In my field, it goes by the name of the causal wedge, but it's sort of the region outside the horizon. When there's more to the space-time than the causal wedge, there's a horizon. Okay, so that's the key point. Okay, so I mentioned earlier that this diagnostic of when a horizon is present has something to do with randomness. Why am I talking about randomness? Well, again, as I mentioned, the central dogma in my field is that black holes behave like ordinary quantum systems. They have a standard Hamiltonian, standard time evolution, unitary time evolution. But it turns out that this unitary that governs their time evolution for large enough times, t here, looks effectively random. It's very chaotic. Chaos and randomness go hand in hand in some sense. But so this is a picture that's been around in my field for a while, but something tricky about this is that black holes aren't actually random. Black holes aren't actually random, and they are just described by a single choice of a Hamiltonian. And so, so we need a description of black holes that's more well-suited to the fact that they're not actually random. This fact that they're not actually random is important in classical cryptography. Classical cryptographer needs randomness to secure certain protocols, but they might not actually have access to true randomness. They just have access to some mock-up of randomness. And that seems to be what black holes are doing. And in fact, the better characterization of what black holes are doing, to find that, you need to turn to the quantum cryptography literature. So there are these examples of unitaries, or proposed examples of unitary time evolution, which are efficiently generated. This is important because black holes unitary shouldn't be very complicated. Right? It should generate randomness, but it shouldn't actually be very complex to implement. So it's efficiently generated, but it's indistinguishable from a truly random unitary for all simple measurements. Okay, so this actually is the more physical notion of pseudo-random of the time evolution governing a black hole. What do I mean by simple here? Well, in the cryptography literature, simple means you have a certain number of gates, a certain number of bits, qubits that you're allowed to act on. That the number of gates and bits doesn't scale exponentially in the entropy of the black hole. Okay, so for all observers who are bounded in their computational power, they can't tell the difference between a black hole's time evolution and a truly random time evolution. That's at least the claim. So black hole time evolution should be well described by pseudo-random unitaries. This is the more physical requirement. I should mention that demanding that something is indistinguishable for all measurements, even exponentially complex measurements, is highly unphysical. Exponentially complex measurements are really crazy, and we never have access to them except for maybe tiny systems. And black holes are large systems with many degrees of freedom, so this is really the more physical criterion. Okay, so what does this have to do with horizons? Well, I should mention that this is just an intuitive definition of pseudorandom unitaries. The technical definition is found in recent quantum cryptography literature, so this work actually utilized some recent ideas. Okay, so what does this have to do with horizons? So the idea, what we argued for in this paper, what we showed, is that pseudo-random time evolution on the boundary guarantees that there's a horizon present in the bulk, at least for an overwhelming number of states, meaning you could maybe fine-tune a state to have no horizon, but be well described by its time evolution be well described by the pseudo-random unitary. But generically, overwhelmingly, this will not be the case. So once you have this pseudo-random time evolution, you know you have a horizon. Okay, I'm going to go through this argument. So here's a sketch of the argument. There's a lot more to it than just this, but time is limited. So let U be the unitary that describes the boundary time evolution, some pseudo-random unitary. The first claim that I'm going to, well, state, really, is that there exists an operator whose expectation value in this time-evolved state cannot be reconstructed by one of these simple observers, these observers whose powers are bounded away from exponential complexity. The next statement is that the expectation values of all observers, of all observables or operators lying in this causally accessible region, this causal wedge that I mentioned earlier, all of those are simple to reconstruct. But because there must exist an operator which one of these, so 1 and 2 together imply that there exists an operator which one of these causal observers can't actually reconstruct. And therefore, there must be something more than just the causal wedge. There's an operator outside the horizon. I mean, outside behind the horizon, in other words. There is a horizon. So that's the basic structure. So point 1, to prove point 1, we just piggybacked off the great work of our collaborators, Lisa and Netta, who showed in a pretty cool paper that, so imagine you have some observer who is tasked with trying to replicate this pseudo-random unitary given only computational powers, bounded computational powers, so not exponential powers. They might come up with some algorithm which outputs some guess unitary for what the time evolution is. And what they showed is, given that guess, there always exists some operator for which the expectation value in the true state, time-evolved state, is order 1 different from the expectation value in their guess. Okay? By order 1, I mean there's some constant alpha here, which is independent. Often in ADS-CFT, we like to take this large N limit, where things become classical, so the number of degrees of freedom on the boundary theory goes to infinity, and the gravitational dynamics in the bulk classicalizes. Saying this is order 1 just means that in that limit, this thing remains constant. It doesn't depend on N or G Newton in the bulk, in other words. So there's something that this computationally bounded observer has to get wrong. There's an operator that it has to get wrong. Okay, this is a long paper, and I don't have time to go over the details, but ask my collaborators if you're interested. Okay, so the next step is that expectation values of all operators lying in this causally accessible region, those are simple to reconstruct. So this is almost a piece of canon in my field at this point, but the basic intuition is that when you have an operator in this exterior region, what you can do is start from the boundary. You're one of these simple observers. You go into the bulk. You make some measurements. Maybe it's you and a bunch of your friends. You collect all your measurements, and you fire your rockets and come back out to the boundary, and you report what you saw. And it's arguable that doing this type of operation, you can get everything in the causal wedge. There are some subtleties to this statement, but I'll leave them for further discussion later. Okay, but then, as I mentioned earlier, you have these 2 statements. One is that there exists some operator which bounded observers can't measure. 2 is that a certain family of bounded observers can measure everything in the exterior in this causal wedge region. And so there must be something they're missing in these pseudo-random states, which means there's something more than the horizon, than the causal wedge, which means there's a horizon. So that's the sketch of the argument. Okay, the second thing, I want to pivot now and sort of describe the second thing, which is a characterization of singularities, because we would like to answer, so which singularities are actually cloaked? We have a characterization of when horizons are present, but we'd also like a characterization of which singularities actually incur a horizon. And again, this is important because there are these counterexamples, so we need to deal with these counterexamples. These counterexamples have the characteristic that they tend to be small singularities in some sense. So perhaps maybe it's just large singularities which need to be cloaked. Okay, obviously, what do I mean by large? This is in quotes here. That's the key point. So we're going to leverage the fact that we're in ADS-CFT and use the boundary to define a size of the singularity. So we have a small or a large singularity based on whether it's visible or accessible from the boundary for a short or large amount of time. What I mean by that is take some naked singularity, say here, some spacetime with a naked singularity, maybe it exists for some period of time. it has some image of itself on the boundary. Let's call it future image T plus and past image T minus. And the question is about the size of these images. So what do I mean rigorously by the images? Well, T plus, T minus, these are the regions on the boundary for which, they're points on the boundary for which there exists a past in the case of T plus or future in the case of T minus, acoronal null geodesic from P to the singularity. Now there's a subtlety here, which maybe only the experts might complain about, but I'll bring it up, which is that the singularity is not really a part of the spacetime. A characteristic of spacetimes with singularities is that they're inextendable geodesics, right? So, but you would still like to associate to the spacetime some region which is like a singularity, or at least associate to the singularity some topology. This is actually a problem that was solved a while ago by Garrosh, where you can think of taking equivalence classes of inextendable geodesics in the spacetime. So where the equivalence, so here are two geodesic or three geodesics in the spacetime, the equivalence relation is that two geodesics are equivalent if they approach each other as they approach this point, this inextendability point. So in other words, if there's a tubular region around one of the geodesics, such that for any tubular region, the other geodesic enters it at some point, then these are equivalent. You can show this as an equivalence relation. And you can mod out by this equivalence relation. This defines effectively points, and there's a natural topology induced on this set. And you can sort of this way think of the singularity as actually being a part of the original spacetime in some sense. So having done all of that, you can now go and compute what this T plus and T minus images are. And then you can define the size of the singularity just to be the min of T plus and the size of T plus or the size of T minus. So min of the size of T plus, size of T minus, where the size of T plus or minus is just the proper spacetime volume of T plus and minus in the boundary metric. For experts, there's some kind of conformal ambiguity or really a units ambiguity on what we mean by the size, but we don't really care because we just mean, we just will care about how it's scaling with various parameters, which I'll come to in a second. But here are sort of three examples that you might consider. So in this first example, this is the one that I just showed. Here you get some non-zero answer. And this is the more standard evaporating black hole example. And you see that while T minus is large, T plus will be tiny or negligible in this case, which is what you would expect. And here's a black hole that violates strong cosmic censorship. Again, this will be a very small answer for the size of the singularity. Okay, so what are the large singularities? Well, large means that this size, scales inversely with the Planck length, or as you take the g Newton to zero limit, holding all the other scales fixed, this size, if it blows up, that's a large singularity. It's a classical singularity. It's there in the classical theory. And these are the singularities that we would like to rule out. Everything else we'll call Planckian or semi-Planckian. I don't have much time to explain semi-Planckian today. But you can ask us after the talk. So what's the upgraded statement that we're proposing? So the upgraded statement of quantum cosmic censorship is that boundary states, at least in ADS-CFT, boundary states which are dual to some geometry do not typically have classically naked singularities. So these large singularities. And typically, well, you might want to discuss what that means. But I'll leave that for later. Good. So that's the statement. But to connect these two parts, well, you might hope that there's an argument for this quantum cosmic censorship conjecture. And well, what our dream was, which we didn't fully flesh out, is that somehow classically naked singularities are associated with boundary pseudo-randomness, whereas these small singularities or Planckian singularities are not. Fortunately, we don't know enough about the dynamics of singularities to conclude anything along this front, but I turn it over to all of you to teach us about singularities in general relativity, naked or otherwise, I guess. Okay, there was a lot I didn't say. This is just, I'm just flashing this to emphasize that this is the theorem statement of cryptographic censorship. There are a ton of terms in here I didn't mention. I really gave it, when I said I was giving a sketch, I really meant a sketch. So you should come talk to us if you're interested in the details. And to help you find us when you want to come talk to us, here's a totally normal, not embarrassing picture of us so that you can find us. And that's, yeah, that's it.
Thanks, Adam. We have time for a couple of questions. Let me. Oh, sorry. I think I'm supposed to give you a microphone.
The existence of a horizon was associated with the behavior of OTOC. So what's the connection with this? Are they equivalent?
Yeah. The idea would be that, so the decay of the OTOC is also related to the unitary becoming an approximate K design or approximate 2 design or higher point design. And the idea would be that pseudo-random unitaries obey those properties. So they, so the decay of the OTOC would be a signal that you're approaching a pseudo-random unitary. Or it's a necessity for you to become a pseudo-random unitary. It's a good question. I would need to think about it. There's a lot we don't know, but I think not, yeah. But yeah.
Julian or Ben, either way. You can find it out.
Hi, thanks. A very nice talk. There's one step which I probably didn't follow, which is that to go from this cryptographic story to an actual story about black holes, you need some manifestation of pseudo-randomness or complexity of time evolution. So what is the gravitational manifestation of that?
Yeah, we don't know. Yeah, I didn't address that because we don't know the answer, but we would love to know the answer. Yeah.
It's maybe a little bit related, but I missed. So you have this operator that's not well reproduced.
Yeah.
But then how do we know that is some kind of low energy type of thing behind the horizon and not just some kind of thing that's not captured by supergravity?
Yeah, because that's in the details of the argument in the paper, but we had an argument that this is getting into the weeds a bit, but as you take the n to infinity limit, you can argue using Lisa and Netta's paper that operator exists sort of in the large N algebra of operators at infinity. And so we expect it to have a dual that's in the low energy effective field theory. But yeah, that's the basic argument.
Noah?
In the beginning of the talk, you gave some examples of systems that break weak cosmic censorship conjecture. Maybe this is comparing apples and oranges, but are there any examples, like now that you have cryptographic cosmic censorship, do you see that like there are examples that break the weak cosmic censorship, but they obey this? Or?
We don't understand enough about the structure of singularities to say anything concrete there, but yeah, we would expect that these short-lived singularities that are visible only for a short period of time don't exist around, they're not around long enough to get you the type of randomness that you would need. So we expect those to not violate this.
Are there any further questions? Yeah.
Yeah, so 100 years ago, people were really bothered by the appearance of singularities in general relativity, especially including Einstein. And I think a modern point of view on that would be that all theories are approximate. We go on to better theories. It's just telling us that general relativity breaks down somewhere. And as you mentioned, it's a problem for observers because it would be great if general relativity would break down somewhere and we could do measurements. But then Penrose came along in the mid-'60s and said, yes, there are there are singularities in general relativity, but they're always hidden behind event horizons. And annoyingly to me and to observers, that's, even though his precise statement has been disproven, it's almost true, and there's probably some version of it that is true. And so the question is, why should it even be almost true? And what I'm wondering is, and there's been a vague words bandied about that it has something to do with general relativity is dual to thermodynamics, but does your work give us any insight into why cosmic censorship is almost true?
Well, because we didn't prove something like almost cosmic censorship, I can't say for sure, but what I will say is that what we expect to be true is that this is what I alluded to in this slide, that there will be whatever you're going to prove, there's going to be some notion of typicality that you're going to need. And we saw this in our cryptographic censorship discussion, where there might be very fine-tuned state. It showed up mathematically that there could be very fine-tuned states that actually violate the bounds that we're showing. But typically, that won't happen. And so that's when you go to prove the statement, there's some measure on the set of states that you need to consider, and it'll be order 1 in that measure that obeys your bound, but maybe with very small probability it violates it or something. So if you randomly pick a state, you might get unlucky. That's possible. I don't know. Yeah, I don't have a better answer than that.
Okay, thank you.
Sure, let's do it.
Yeah, one thing, I mean, there's nothing time asymmetric in your arguments or results. So if these, cryptographic conditions held, there's no reason why you would expect a black hole rather than a white hole.
Yeah, that's a great point. Yeah, no. Strictly speaking, all we proved.
Whereas, depends how you formulate it, but very strongly in the background of weak cosmic censorship is the idea that you shouldn't allow white holes, but black holes would be fine. It's not in the formulation as you gave it, where you're starting from good initial conditions, but certainly in the general thinking, the idea would be black holes are perfectly fine, according to people who would believe in weak cosmic censorship, but white holes should not be allowed.
Well, white.
This is only a comment, it's not an argument.
I think that might relate to this previous discussion, because in white holes we expect to be very finely tuned in some sense.
But there isn't
object.
Anything in your results
No.
that say that there should be any difference.
Correct. Or not that I'm aware of. I don't know if my collaborators.
Let's talk about it over lunch. Great. Okay. Thanks a lot, Adam.
Yeah.
And for our final speaker of this morning session, before we let you go off to have lunch, is Manus Visser. He's a postdoc at Cambridge University across the pond, but he'll be starting as a faculty in Nijmegen in the Netherlands in the fall.
Thanks, Evita, and thank you to the organizers. This is my first time in Boston, and it's a pleasure to be here. So this talk will be on the foundations of black hole thermodynamics. So the laws of black hole thermodynamics belong to the most remarkable discoveries in modern physics, arguably, since they combine general relativity, quantum field theory, and thermodynamics in one overarching framework. So in the 70s, Bekenstein, Hawking, and others showed that black holes are genuine thermodynamic systems with an energy, a temperature, and an entropy. However, black hole thermodynamics poses certain conceptual puzzles, since it contains features that are seemingly different from standard thermodynamics. And some philosophers, notably Doherty and Callender, have argued that these features suggest that black holes are not really thermodynamic. And what I will do today is that I will highlight two different puzzles in the foundations of black hole thermodynamics, and then I'll try to explain for non-experts how holography resolves these puzzles. So one of the main motivations for black hole thermodynamics is the so-called no-hair theorem. So the theorem states that stationary... Yeah. Yeah. There you go. So stationary exisymmetric black hole solutions can be characterized completely and uniquely by three classical parameters in GR plus electromagnetism, so the mass, angular momentum, and charge. And this is reminiscent of equilibrium states in thermodynamics, which are also characterized by only a few macroscopic variables, like the internal energy, the volume, and the particle number. So stationary black holes are analogous to thermal equilibrium states. Now, Bekenstein argued that black holes should carry an entropy proportional to their horizon area in Planckian units. And notably, the black hole area scales not with the volume, whatever that may be, of a black hole, but with the horizon area. And therefore, it's not extensive, like in standard thermodynamics. So the first puzzle is why does black hole entropy scale with the horizon area? So Bardeen, Carter, and Hawking derived 4 laws of black hole mechanics, which are analogous to the laws of standard thermodynamics. And I want to highlight mainly the so-called first law of black hole mechanics, which is equivalent to the first law in thermodynamics, or more properly called the fundamental equation in thermodynamics, which is dE is TdS minus PdV, or plus more work terms. So in black hole mechanics, the first law relates the change in the mass of the black hole to kappa delta A, where kappa is the surface gravity. So this term is interpreted as TdS. And then you have, for instance, an omega dJ, which could be interpreted as a chemical potential times the charge. But there's no PDV term in black hole mechanics. So the second puzzle is, where is the PDV term in the first law of black hole mechanics? Now, the main thesis of today's talk is that holography resolves these two puzzles. So, as Adam already explained before, in gauge gravity duality, or in holography, black holes in a bulk geometry are dual to thermal states in a boundary quantum theory. And crucially, these thermal states satisfy the standard laws of thermodynamics. So what I will do in this talk, I will explain explain a dictionary, a holographic dictionary that relates the kind of non-standard laws of black hole mechanics to the standard laws in the dual theory. Okay, so the naive picture of holography is that due to the area entropy relation for black holes, the degrees of freedom kind of live on the boundary in quantum gravity. But some more precise versions of the holographic principle are that, there are kind of two forms, and already 't Hooft and later Susskind mentioned or conjectured these two different forms of the holographic principle. So the first form is what I call the weak holographic principle, or rather the entropy bound, which states that any theory of quantum gravity should exhibit an upper limit to the total number of degrees of freedom in a spatial region with a boundary B. And the upper limit is given basically by the exponent of the Bekenstein-Hawking entropy. So the strong version, however, states that quantum gravity is dual or equivalent to a quantum theory living on the boundary of the bulk spacetime. So GR in the bulk is equivalent to quantum mechanics on the boundary. And I should emphasize that it's a big leap to go from the weak form to the strong form. However, we do have a precise version of this strong form, which I'm going to discuss now, which is, of course, the ADS-CFT correspondence. So that relates a weakly coupled gravity theory in a bulk asymptotically ADS spacetime to a conformally invariant gauge theory at large n, so large rank of the gauge group, and at strong coupling living on the conformal boundary of this spacetime. And what's important for us is that black holes in the bulk are dual to thermal states on the boundary. Now, I need one important dictionary here, which relates the cosmological constant to the number of degrees of freedom, or rather the central charge of the conformal field theory. So the cosmological constant is related to the bulk ADS radius in this way, and the cosmological constant in the bulk is related to the number of colors, or rather the central charge of the CFT, which is a measure for the number of field degrees of freedom, through this formula. So the central charge of the CFT scales with the area of the bulk radius divided by Newton's constant. Okay, so let me now come back to these puzzles. What's the origin of the area scaling in holography? So naively, you might say, well, a spatial volume on the boundary is an area in the bulk. So it seems that the Bekenstein-Hawking entropy is extensive in the CFT. But I think this argument is too naive, because actually in the CFT, thermal entropy is not necessarily extensive at finite temperature and finite spatial volume. Actually, in fact, on the boundary, in a deconfined phase of a large N gauge theory, the thermal entropy scales with the number of degrees of freedom, so the central charge, or n squared in like an SUN gauge theory. So it doesn't scale with the volume, but rather with this central charge C. And in the bulk, this matches precisely with the Bekenstein-Hawking entropy, because this is like RH is the horizon radius, so this is the area of the horizon. And so if you divide and multiply by L to the d minus 2, you see that the Bekenstein-Hawking entropy is indeed proportional to the central charge. And what's interesting is that in the large volume or large temperature limit, this entropy becomes extensive. So it does, in that case, it does scale with the volume. So let me now compare this to, so this was about black hole thermodynamics, but let me now compare this to standard thermodynamics. So in standard thermodynamics, the entropy and energy are extensive. So the energy satisfies this, is a homogeneous function, and it satisfies this relation, which is an extensivity relation. So if you rescale alpha in the arguments, then the energy scales in this way. And so from this scaling relation, you can actually derive what's called the Euler relation in thermodynamics, which relates the different variables in thermodynamics. So if you take the derivative with respect to alpha, you set alpha equal to 1, you get this so-called Euler relation, where the conjugate quantities, so like the temperature, pressure, and the chemical potential, this is, so B here is a conserved charge, and nu is a chemical potential associated to that charge. So these conjugate quantities are defined through this first law. So you need to use this first law in order to derive this from the scaling relation. Okay. But notably, you see that there is a PV term in this formula. However, in holography, I will now show you that you don't have a PV term, precisely because the entropy is not extensive. So in large N gauge theories, there is, on compact spaces, there is a deconfinement phase transition. So in the confined phase, the energy is proportional to an order 1 number, so n to the 0, order n to the 0, whereas in the deconfined phase, the energy and entropy and all the conserved quantities are proportional to n squared. And this is very important, because that was actually related to the area law scaling, the Bekenstein-Hawking entropy. So because of this scaling, there is a scaling relation again for the energy, but now the volume doesn't rescale. So this energy function is not homogeneous, it's not extensive. It's a homogeneous function, but it's not extensive. So from this scaling relation, again, you can derive an Euler equation, but now there's no PV term. But on the other hand, there is a mu C term, where mu is the chemical potential associated to the central charge. And what's interesting is that if you go to very high temperatures or large volumes, you recover the standard Euler equation, because in that case, mu c becomes equal to minus PV. All right. So what I want to now explain what is the dual relation of this large N Euler equation. So this is maybe for experts, but there is a so-called SMAR equation in the bulk, which relates the thermodynamic the black hole parameters, basically. But what's interesting is that you have these d-dimension dependent factors in this SMAR equation, and one can show that this SMAR equation is precisely equal to the Euler equation that I showed before. And moreover, there is, as I said before, there's a first law in black hole mechanics that relates the variations of the different parameters. And what I want to explain now is how, that this is actually dual to the first law, the standard first law in the CFT. And notably here, there is a PDV term and a mu-dc term. So even though there's no PDV term in the bulk, there is a PDV term on the boundary, which explains this or resolves this second puzzle. So let me now go through this in more detail. So the first law in the bulk relates the variation of the different parameters. So these parameters you are probably familiar with, but this is kind of a new term which many people have studied before. So lambda here is the cosmological constant. So you're changing the theory here, and theta is the conjugate parameter to lambda. Now, this kind of extended version of the bulk first law can be rewritten so that it matches precisely with an extended version of the boundary first law in the CFT by using this holographic dictionary, which is a very standard holographic dictionary. So V here is the spatial volume on the boundary, and E is the energy on the boundary, temperature, kind of angular velocity, and a chemical potential for charge. But this match only works if this pressure satisfies the CFT equation of state, and if this chemical potential associated to the central charge satisfies this Euler equation. So you can see that these equations kind of arise naturally by matching the bulk and boundary first law. And also, as I said before, this PDV term arises naturally on the boundary, even though it's kind of not present in the bulk. Also, if you're bothered by saying that I'm changing the theory here, so this C also changes the theory, whereas in standard thermodynamics you're not changing the theory, you're only changing the state, you can actually fix this C and this lambda, but this V will still be present because there is a difference between the boundary curvature radius and the bulk curvature radius. So there's a difference between R and L. Okay, now to summarize, what are the resolutions to these puzzles? So the first puzzle was, why does black hole entropy scale with the horizon area? Well, that's because black hole entropy in ADS-CFT is dual to the thermal entropy of a large N gauge theory in the deconfined phase, where the entropy scales with the central charge, or a number of degrees of freedom. And this central charge satisfies a dictionary which relates it to the area of the bulk radius. The second puzzle was, where is the PDV term? Well, it's present in the CFT first law. So some concluding remarks. Holography kind of resolves some of these puzzles in black hole thermodynamics, and there are, of course, many other puzzles like the black hole information paradox, which I didn't touch upon, but holography also has a lot to say about that. It's a heuristic principle that is very useful still in ongoing research in quantum gravity, like Mach's principle maybe, and the equivalence principle aided in the development of general relativity. And I only talked about holography for ADS spacetimes, but holography for non-ADS spacetimes is also still an ongoing research topic. So let me stop there and take questions. Thank you.
Thanks, Manus. We can start with a question from Pia. Very nice talk. Could you explain a little bit where you pulled the lambda term from in the bulk?
Right. So what's important is that in this lambda term necessarily appears in this so-called SMAR equation. Like for asymptotically flat black holes, this lambda is 0. So there it doesn't appear, but here it has to be there, otherwise this relation doesn't hold. And then what you can do is you can use a kind of homogeneous Euler theorem to relate this SMAR relation to the first law, where you have to vary each of these parameters like m, a, q, and then lambda, and then you get this relation without the dimension-dependent factors. That is one way to derive it. There are many other ways. But it is true that you're changing the theory, which is a little weird. But so I should say that these people have actually worked on a different interpretation of this lambda term in the first law. So they interpreted this lambda as a bulk pressure because it's like a perfect fluid, and then this lambda is the pressure. So they viewed this as a VDP term. So so it's not a PDV term, but VDP, and that means that they said, well, M is the enthalpy and not internal energy, which I always found weird because in ADS-CFT, M is just total energy, it's just internal energy and not enthalpy. So that's why I kind of came up with this other holographic interpretation.
And this is not a unique modification, right? You could add in other terms with other interpretations.
Like what kind of terms? For other black holes, you have other parameters, and then you have extra terms. But I think it's quite unique for these black holes.
Yeah, hey. Sorry, it's loud. I'll try to hold it far away. So I'm really confused about your use of the word extensive. So, for example, you said that at fixed volume, the free energy is not extensive. But that sounds tautological to me, because what extensive means is that when you scale the volume to be large, the free energy scales with the volume. And in fact, I can say it even more precisely. So here we're doing CFT. We should only talk about dimensionless things. So what we mean is the volume in units of the temperature. I only see two parameters, right? The central charge and the volume in units of the temperature. And extensive means when the volume in units of temperature is large, then the free energy is like the volume. And that's true. And that's it. I mean, I don't see any, what's the problem? I don't see a problem that needs to be solved. I don't see anything that's not extensive.
I think so what I mean by extensive is this relation. But I think at finite temperature and volume, the entropy is not necessarily extensive. So
but what does that mean? Extensive means it scales as the volume is big. If you say at finite volume, it's just, the free energy is just a number.
Well, okay, by extensive, I mean this relation. So it could hold at finite volume as well.
But aren't you changing the volume on the left side of that equation?
Right, but it does not necessarily hold for large volumes, right? This relation holds for finite volumes in thermodynamics, whereas in CFTs it only holds for
No, not in general, right? No, it holds for volumes which are large compared to the temperature. If you have an oven and you can have the volume be small compared to the temperature, this will not be true. It's true when the volume is large compared to the temperature, or the thermal wavelength if it's a non-relativistic gas.
Okay, I'm not entirely sure that's
I mean, I think a CFT is just like an oven. There's no, I mean, for this kind of point of view, it's no different than the oven. It's just as extensive as the oven, no more, no less.
Right, but it is true that black holes have an entropy at finite temperature. So, and those are dual to a thermal entropy in the CFT. And in that case, this relation doesn't hold.
Well, it holds when it's supposed to.
That's fine, but okay, maybe you don't agree with the terminology extensive, but like this scaling relation doesn't hold for finite temperatures and volumes. And actually this scaling relation does hold. And what I tried to explain is where the area relation comes from. That it comes from the n squared dependence and not from the volume.
Yeah, I had a question about, oh, it is loud. Yeah. I had a question about adding a chemical potential for the color. Let's say you wanted to do that in Moltesena's original example. Don't you need to find the appropriate, like, Hawking-Ross terms for the 5 form in 10D? I mean, can you actually do this in supergravity such that this relation with the new chemical potential actually comes out? Because it would seem like you need some way to, dynamically change higher form charge. Perhaps in ADS3 this makes sense, but can you do this in Moltesena's example, for instance?
Yeah, I think you have to add some extra ingredients and change some kind of flux that changes this n squared.
Yeah, you need the appropriate boundary terms for the 5 form, which is, I don't know if those are known. But that's why I was asking if you knew this.
No, I haven't. This is an open question. I haven't worked on.
Yeah.
Nella?
Is this far enough? Okay. Yeah, so you motivated this from the second law of thermodynamics, but the second law is only non-trivial when you have actual dynamical black hole. And for a dynamically evolving black hole, the area of the event horizon is not dual to a CFT entropy. In fact, you have pure state black holes in the bulk, and they have 0 entropy, and yet they have a non-zero area, and this is not explained in any way by CFT entropy. You can also talk about non-time evolving black holes that are single-sided in pure state, and that are stationary, so in some sense they fit into some of your parameters here, but they still have 0 entropy.
Mm-hmm. 0 thermal entropy, but finite entangled entropy, you mean?
I mean, they have a 0 von Neumann entropy, pure states.
Right. Yeah, I guess I was thinking mainly about the first law and the how the entropy there arises from thermal entropy in the CFT. So for single-sided black holes.
But even for the first law, you have to perturb the system a bit. And as soon as you perturb the system, then the area of the event horizon doesn't actually mean entropy in the CFT.
Well, if you perturb between 2 stationary states, then yeah, so that was the setup I was thinking about.
And if the states are stationary, they could still be pure states and not actually have an entropy in the CFT.
Okay, but so entropy could, in 2D CFT, for instance, could arise from the Carr formula, right, which arises from mixed states. So.
Yeah, so you need some very special type of black hole. Otherwise, the black hole is in a pure state, and then the Carr formula doesn't, you're just going to give you 0 for the von Neumann entropy.
Right. So you're saying there is a different origin, maybe, for black hole entropy?
I'm saying ADS CFT doesn't compute the area of the event horizon of black holes, except in really special cases.
Okay, maybe one more quick question, and then we can wrap up for lunch.
Hi. So I was actually just wondering. So you briefly went over this. You said that there's this weak form of basically ADS CFT, and then you said the strong form, and you said the weak does not imply the strong. I was wondering if you could say more about. Yeah, it seemed like you had some more on the side. I was just wondering if you could say a little bit more about what we know about the relation between the two, if anything.
Yeah, I don't think there is a relation. So what I mean by the weak form is the entropy bound. So for the most precise version is the covariant entropy bound, which you can prove in semi-classical gravity without using a duality. So by just using the Einstein equations and Ricciardo equation, for instance. So that's what I wanted to highlight, that if you think about the holographic principle, in terms of an entropy bound, that doesn't really imply a duality, whereas I think we do believe the strong form holds, but it doesn't follow logically from an entropy bound.
Okay, thanks.
Great. Let's thank Manus again.
I hope you had a wonderful lunch. Our first speaker in the new session is Dr. Sara Issaoun. Sara is a Einstein Fellow at the CFA and is here to tell us about the first polarized image of our Milky Way black hole. Sara, take it away.
Thanks, Daniel. All right, so I had the pleasure of being one of the co-leads of this project alongside Angelo Riccardi, so I'm very excited to tell you all about our newest results from the Event Horizon Telescope collaboration. So first, the usual caveat, I'm speaking on behalf of a 300-plus member collaboration spread across 60 institutes, 20 countries in Europe, Asia, Africa, North and South America. A bunch of us just got back from our collaboration meeting that's annually held, and we were just in Mexico City. Most of us flew back a couple of days ago, so here are 2 group pictures from the meeting. All right, for people who are not too familiar about the Event Horizon telescopes, we're a virtual network of radio telescopes connected to form a telescope the size of the Earth. So we record data onto hard drives at different sites and then ship those data to a correlation facility that plays it back and aligns all the signals from the different telescopes. At the calibration stage, we finally synthesize the telescope the size of the Earth from that data, correct additional calibration issues in the telescope data, and then finally average down all our data to make the best data product to be used in imaging. And then our imaging softwares then take the data and try to recreate an image that best matches the data properties and various information that we input about our knowledge of the source that we're trying to image on the sky. So in order to image with the Event Horizon telescope, we use a technique called aperture synthesis. So because we have only, at the time of these observations, 8 telescopes on the ground, we have a lot of gaps in our virtual mirror. And we fill these gaps using the Earth's rotation. So the Earth's rotation fills our virtual mirror as we can combine data on multiple temporal and spatial scales. So as the Earth rotates, the separation between 2 telescopes has a different projection along the source line of sight, and then we are able to get more spatial scale information through that projection changing over time. And then as we stack data over time and spatial frequency, our image improves more and more until we get our famous first image of a black hole that we released back in 2019. So the EHT is, of course, famous for these 2 images. We observe a wide variety of other sources, the active galactic nuclei, but these are really our horizon sources, the sources at which we can image the shadow of the black hole created by light lensing around its event horizon. And so we have 2 sources that we primarily look at with the EHT for this kind of science. First is M87 star. This black hole is 55 million light years away from us. It's 6.5 billion solar masses. It's one of the biggest black holes in our known universe. And M87 is particularly interesting because this black hole, because it's so large, it sits in a pretty old galaxy, a giant elliptical galaxy. And it spews a huge jet of matter. In fact, is the first astrophysical jet ever observed back in 1918 with an optical telescope. And this jet crosses, kiloparsec scales across and out of the galaxy, and it's a powerful blast. And this black hole is essentially one of the few in our known universe that creates these jets that are bright enough for us to see. And so it's a very special black hole in that case, in that we can learn a lot about this jet mechanism from looking very close to the black hole, because this is where this jet originates. The black hole is the engine that powers this jet. Then we have another black hole, Sagittarius A star, the topic of this talk today. Sagittarius A star is 27,000 light years away from us. It's very close because it's at the very center of our Milky Way. It's 4 million solar masses. It's much smaller than M87 star. And in fact, here's, in M87, we also looked at it in polarization, and polarization gave us even more information about the properties of the gas around the black hole. And now we're kind of switching over to Sagittarius A star, and I'll tell you about what polarization teaches us for this source. So just to give you a sense of scale between the 2 black holes, Sagittarius A star fits very snugly inside the orbit of Mercury. whereas M87 star can engulf our entire solar system up until where Voyager currently is. So the size scale is really different between these two black holes. And in fact, it makes Sagittarius A star a lot more challenging to look at. M87, because it is so large, light moves around the black hole very slowly over a few days. And so when we're looking at it for 8 hours of observation over one night, and we're using this aperture synthesis method, we're trying to stack data over several hours, our image on the sky of M87 essentially doesn't change. It doesn't move. So we're stacking data on a static image, which is perfectly fine, and then we're able to reconstruct this image very easily. This is why this was the first one that we published. Sagittarius A star, on the other hand, because it's much smaller, light can move around over the span of a few minutes. And so in that case, if we're trying to stack data over 8 hours, our source is just constantly wiggling and changing all the time, which makes this a much more challenging object to get an average image of, and a sense of what it looks like on average. But we managed that feat and released this image in 2022, and now we're going to add on polarization, which also deals with similar challenges. This doesn't play. So what do we know about polarization of Sag A star in the historical context? So the unresolved polarization of Sag A star has actually been studied intensively over the past 2 decades. In 1999, there was the first detection of circular polarization at the low-frequency radio or long-wavelength radio with the VLA. In 2000, there was a tentative first detection of linear polarization at the higher frequencies or short wavelengths with the JCMT. This lack of Faraday depolarization in the data caused an accretion estimate for Sag A star to fall by 4 orders of magnitude to about this 10 to the minus 8 solar masses per year. This is a very, very low accretor, much less than M87, for example. Then, 20 years after that, there were many detections of linear circular polarization and also rotation measure in unresolved measurements. Linear polarization was actually not detected below about 100 gigahertz, and it's about 5 to 10% at the higher frequencies. Circular polarization stays pretty low, between 0.1 and 1%, and always negative, and always slightly rising with frequency. And the rotation measure stays at roughly this negative large value of minus 5 times 10 to the 5 radians per meter squared, but the rotation measure is also very, very variable over time. Then there were proto-EHT observations, so EHT observations while the array was still forming, that were carried out in 2013. And these are the only observations, well, until this result, that resolves the polarization in Sag A star at any wavelength. And what these results told us, if we're looking at polarization on various pairs of telescopes that probe different spatial scales in our image, what we're seeing is that there's very, very strong polarization on long baselines, on very, very small spatial scales. And we're seeing asymmetric polarization between what the different pairs of telescopes are probing, which means that there's spatial changes in the polarization direction on our image. And these observations also showed that Sag A star has strong polarization variability, and it was a valuable model constraint for our simulations using general relativistic magnetohydrodynamics, or GRMHD. As a quick summary of the history, so polarization observations have provided some of the most significant breakthroughs in understanding the accretion flow of Sagittarius A star over the past couple decades. They were decisive in establishing Sag A star as an extremely underfed black hole, and especially much more underfed than M87, that is also fairly underfed as a black hole. It was the best window to variability for Sag A star that we had, and we had multiple lines of evidence for a persistent, partially ordered magnetic field structure near Sag A star. And unlike M87, there are actually almost no previous polarimetric measurements of Sag A star using VLBI because of various challenges in detecting this signal. So this is what our current EHT campaign looks like. If you remember what it looked like for the proto-EHT, we have, of course, many more telescopes, and so many, many more pairs of telescopes that are probing different spatial scales. So this is our data for Sagittarius A star for April 6 and April 7, 2017. And what we're seeing here is, of course, many different pairs of telescopes probing spatial scales that have very different polarization. And the longer baselines are the smaller spatial scales, and so we're seeing much more polarization on smaller spatial scales and weaker polarization on larger spatial scales. And so now we have to take all this data and reconstruct a polarization image. And how we do that is along two fronts, diversity and redundancy. So as per usual for EHT results, we have a variety of different methods developed for EHT imaging. And in this case, we used 4 independent methods that have very, very different ways of analyzing polarization data. These are the names of the 4 methods. So I won't go into too much detail about what they're about, just kind of going over how diverse they are. So the 4 methods have different bases of either pixels or wavelets or rasters or a geometric model of a ring, because we know Sagittarius A star is a ring from our total intensity previous results. The methods also use different data products as their basis for imaging. Some make independent images of the different Stokes parameters, so they make a total intensity, a linear polarization, and a circular polarization image separately, and some combine all of them to make just a full Stokes polarization image. They also handle the variability in Sag star differently. So 2 methods essentially use a budget for the variability in the data and try to make an average image from that data, whereas these other 2 deal with variability after the fact. So they make snapshot images over one night of observations and then combine all those snapshots into an average image. And then they have also different results in how they come up with a final image. So the first 2 we call regularized maximum likelihood methods. They essentially create a survey of different buttons in the software as different parameters that are optimized on synthetic data and then create a final image that way. And the other 2 have a posterior exploration method in which they have full posteriors of different range of images that is obtained with the software. So many methods that we have different assumptions about the image, different data products that they're using, different variability mitigation, and different image products that they end up with. But wherein they agree is that what we see are signals on the sky, not artifacts of the analysis. So these differences actually help us pinpoint which features in the image we are most confident about. So in how we do this is pretty common for EHT. So after our data calibration stage, we go through a blind imaging step with independent teams in which we have a feedback on data quality. We move on to pipeline building per independent software. And in this pipeline building, we use synthetic models that are designed to mimic data properties of Sagittarius A star in total intensity and polarization. And then we validate our images against how well they fit the data, how consistent they are to the other sources we're observing, and how robust the structure is to different changes. So this is what Sagittarius A star looks like for 4 different softwares. So the top 2 are primary analysis methods, which have full posteriors, giving uncertainty margins for our theory analysis. I'll talk about that a little bit. And then we have our imaging methods cross-checks down here. So what we're seeing is that all methods are getting most of the polarization across almost the entire ring, which is very different from M87. And it's also quite polarized. And we're seeing polarizations of like 20, 30, 40% on the ring, which is also very different from M87. M87 only went up to 15% at the peak. Sagittarius A star is very polarized. What is also especially surprising is that the polarization direction that we're seeing, these ticks, are very, very, very stable along the ring. And we're seeing a spiral pattern along the ring for all methods. And then we average all these methods together to make our final image. This is what was published. And you see, again, this very nice spiral pattern of the EVPA, of the polarization direction on the ring, and that most of the ring is really polarized. We also looked at circular polarization for Sagittarius A star, and these are our first circular polarization images of Sag A star. And here we have a little more discontinuity between the softwares. All methods were able to reconstruct a negative circular polarization on the west side of the emission ring here. Both our primary methods were able to get a east-west dipole structure along the ring, but our imaging methods were unable to constrain the other one, the other peak. Overall, all the models seem to prefer a very simple circular polarization structure, but we have more uncertainty here than in the linear polarization structure, so this is not very strongly used for theory models. So in order to understand what our images look like, we use this technique of Fourier decomposition of a polarized ring that was work done by Daniel, George, and Ben. We use these beta modes, which are essentially decompositions of the EVPA pattern along the ring. And the two ones that we use the most, this is beta 1, this first order asymmetry on the ring, and this is beta 2, which is rotational symmetry on the ring. And then we have a number of other parameters that we measure from our image, such as unresolved and resolved linear and circular polarization fractions. So here's how our methods fare on the measurements. So these gray bands are the ALMA measurements for Sag A star during the observation. So you can see just how variable Sag A star is also in polarization. That's a huge range. And then we see the measurements for all our different methods. The one I want to make you pay attention a little bit more is this angle of beta 2 here, which is essentially the twistiness of the spiral pattern that we see. And we see very strong agreement between our results and especially our primary result methods that give error bars for theory. So this is Sagittarius A star. This is kind of the common VLBI display of it. And then this is Sagittarius A star in our beautiful field line imaging. So now I'll go into the theory paper, so I led the observational paper and Angela led the theory paper. So Sagittarius A star has a very low accretion rate, which implies that it has a puffy, hot accretion flow. What we're measuring is synchrotron radiation, which is intrinsically polarized and tracing the magnetic field it originates from. The non-polarized image already told us information about Sag A star. It told us that Sag A star prefers models that are non-zero spin, that are relatively face-on towards us, and strongly magnetized. And what's new is that we're seeing large polarization fractions in Sagittarius A star with rotational symmetry of the EVPA pattern. So our theory teams create a bunch of theory models using two methods. First, they evolve a magnetized torus of gas in a Kerr spacetime of a given spin using GRMHD models, and then they ray trace that by solving the null geodesic equation of light trajectories, and then do polarized radiative transfer to get the polarization image that comes from these models. Oh, this is when I have to switch out to the video. Hopefully this works. All right, so in total intensity, we have two models here that look basically identical. So if you were to blur it to the resolution of the EHT, it would essentially also look even more difficult to tell them apart, these two models. Is there a way to speed it up? It's going a bit slow. Yeah, here we go. It's blurred to the resolution of the EHT, so then it's even more challenging to tell these two models apart. But if we switch on to polarization, suddenly they start looking very different. Here we have more radial patterns, and here we have more spiral patterns. So these ticks mean more polarization and less polarization in tick length, and then the color red is more polarized and blue is less polarized. We're seeing quite a lot of differences between these two models. And so polarization is actually a very strong discriminant for the kind of model that we have. In fact, this one has a hotter flow and this one a colder. If we switch to circular polarization also, we can tell the difference between two models very strongly. So red means we have a rotation this direction and blue in the other direction. And so circular polarization also can tell the difference between whether the magnetic field is pointing out towards us or pointing into the board. So here's a kind of overview of the models in dynamics, but if you were to make an average image, these still hold. So average images still carry out information between models and are able to successfully discriminate between them. We're getting there. How do I go back to this one? Okay. Oh, this was another video. Sorry, PowerPoint did not. All right, so this video we also designed for this release. So if you have circular shaped kind of loop magnetic fields, and you have light emitted from synchrotron radiation of hot electrons swirling around these magnetic field lines, what kind of image that we get is kind of spokes on a wheel going outwards into in this direction. This is what the EVPA pattern that we'd collect look like. Now, if we have more kind of spiraling magnetic field lines, and again, we're shooting light photons from swirling electrons, the kind of spiral image, the kind of image we'd get from the telescope is a spiral image of the EVPA pattern. So essentially, having now seen what Sagittarius star looks like from the observational side, you can sort of guess what it would look like from the theory side. But there are additional plasma effects that make kind of the observations look a little bit different, and I'll go into that in a minute. All right. So additional plasma effects were mentioned. So this is caused by Faraday rotation. So as polarized emission travels through magnetized plasma, the plasma along the way actually rotates the direction of the polarization. And to undo this, we need to derotate by assuming this rotation is happening in an external screen between us and the black hole. For Sagittarius star, we observe a rotation measure corresponding to about a 46-degree rotation. However, we're not sure if this entire rotation actually comes from an external screen to be removed. So we need to do the analysis twice, essentially. So we have two images of Sagittarius star. One is the one as observed, which implies a counterclockwise inflow of the gas, and one in which we have derotated by this 46 degrees, which implies a clockwise inflow. So this makes quite a big difference in how we analyze the data. So we have an extensive model library created by a theory team that changes parameters accordingly, looking at different black hole spin, different inclination, different magnetic field strengths, different types of magnetization of the disk, different magnetic field polarity, and also electron temperature. And then we use all our data parameters that we measure to constrain this big library of models. So if we don't derotate, we just take exactly what we see on the sky, the preferred models that we get actually are moderately inclined, rotating counterclockwise, mostly this magnetized arrested disk, so highly magnetized disk, and inconsistent, and this is inconsistent with total intensity constraints. So we did this huge search for total intensity as well, and there were only a handful of models that passed through. But if we do this, there are actually 0 models that pass through if we overlap between the total intensity and polarization. So this is a little bit of a problem, but also exciting for a theorist to have more jobs. Then if we include derotation, suddenly we switch sides, and the preferred models are moderately inclined, rotating clockwise, again, mostly magnetized arrested disk, just like M87. And this is consistent with total intensity constraints for about a handful of models. In fact, our best bet model is this one here, which is a 30-degree inclination of Sagittarius star at high spin. And in fact, if we pick out that model and look at what it looks like, this is the different slices of it in linear and circular polarization. And here it actually tells us where the emission that we're probing actually comes from. And in fact, it comes from the jet, which is very surprising because so many of us probably still believe that Sagittarius A star doesn't have a jet. It's a very, very low accretor, and we don't see one. So I mentioned M87 has this big, bright jet, and it's one of the special black holes. Sagittarius star is just extremely ordinary. It's really boring, and we don't expect it to be as exciting as having a jet. But surprisingly, this model tells us that the significant emission comes from the jet sheath. So we're back at our tale of two black holes, and now we have both of them in polarization. So M87 is a little bit polarized here on this side of the ring, and the polarization pattern is also spiral, and it tells us that it has strong ordered magnetic fields that are able to launch this jet that comes out of M87. So there's a very clear connection between the polarization pattern in M87 and the jet launching from this black hole. Sagittarius A star, surprisingly, looks just the same. It's also very spiral, very ordered magnetic fields, strong magnetic fields, and it seems to indicate that the emission is also coming from a jet that is as yet unseen. So the next adventure for the EHT is, of course, looking at dynamics, because so far we're only looking at average images, and also investigate the possibility of building enough signal to noise, building enough sensitivity, adding more telescopes to be able to pick out the jet emission in both M87 and Sagittarius star images, combining the jet structure with images of the horizon. This is where my talk ends. Thank you very much.
Excellent. Thank you, Sara. We have time for some questions.
Wow.
Excellent. Right over here.
Yeah, thank you for the great talk. So I don't know too much about this, so maybe this might be naive, but your comment about a lot of the emission is coming from the jets. I would expect the jets to be going like in a direction that is not with the light is not coming from that direction to us looking at these images. But then how would, because the jet emissions are highly polarized, but you still say those are the emissions we catch mostly? So I'm a little confused.
Yeah, that's a great question. So this is kind of one of the big mysteries that we have for Sagittarius A star, because so far we have a lot of building evidence, not just from EHT images, but also from infrared, near-infrared observations with gravity, the VLT, that Sagittarius A star is actually pointed more towards us. And so when you think about our place in the Milky Way, we sit in the plane, and the black hole is at the center. And so it kind of goes against some intuition that the black hole should be, pointed, have also its disk along the plane of the galaxy and having the jet pointed out. But in fact, that's not the case. So the scale difference between near the black hole and us outward don't necessarily have to connect. So the black hole's accretion disk and system is only really driven by how the infalling gas closest to the black hole falls onto it. So in fact, there's nothing that tells us that the black hole should really be aligned perfectly perpendicular to our galactic plane. Everything just happens on such a small scale that it really all has to do with how the gas falls in that very, very small environment at the center of our Milky Way. So yeah, just this intuition is very common. Yeah.
Okay. So, but some of my intuition was also that these bright spots are locations of, like from the location of these bright spots, you can infer which direction the black hole is rotating. Is that not the correct intuition?
So these bright spots are likely effects from us having to create an average image from moving matter. Right now, we don't have a really good sense of Sagittarius A star's kind of configuration, because we're averaging over many hours of dynamics that are happening, and we're seeing kind of different bursts of the image and aggregate effects from our softwares that are causing these features. So going into movie making of Sagittarius A star will certainly tell us that answer. We have to see it evolve dynamically and not average out these features, and then we'll get the answer.
Thanks.
All right, one more.
So if I understand this correctly, these the constraints actually hint at an external Faraday screen. That's the derotated ones, right? And then, what about, how does that mesh with like Machek's conclusion in the ALMA observations that it should be internal Faraday rotation based on like the the variability of the circular polarization with frequency?
Yeah, that's a great question. So right now, the fully de-rotated one seems to have an overlap in models. So there's a range at how much we can de-rotate. So the work that's been done with the ALMA data, that you mentioned Maciek's work, that comparing the 1 millimeter data from EHT type observations to 3 millimeter data at longer wavelength, it was found that about half of the rotation measure actually comes from an external screen that's between this scale and a little bit further out where 3 millimeter is probing. So we could rotate it by half and then have a different set of overlapping models. But also the observations that Maciek was looking at are across 2 different days. And Sagittarius A star is variable also in rotation measure significantly over very, very short timescales. So the best way to get that answer is actually simultaneous observations at both frequencies. And in fact, the Event Horizon Telescope is working really hard to making that capability a reality. And then we'd be able to measure, to get that answer, how much of the Faraday screen, how much of the rotation measure is actually external to the scales that we're probing.
Great, thank you.
All right, I saw a few more questions, but I think we are at time. So if folks don't mind, please hold your questions, write them down, and bring them to the coffee break in 30 minutes. So thank you again, Sara. Let's give Sara a round of applause. All right, and our next speaker is Professor Ben Freivogel at the University of Amsterdam at the Institute of Physics, who will be telling us about estimating quantum corrections near black holes.
I'm a bit embarrassed to show my slides after those beautiful pictures of the last one. Mostly I give Blackboard talks, so hopefully this won't be too disappointing. Thanks a lot for having me in this exciting workshop. I wanted to start out with a little bit of democracy. It's fun to use democracy while we still can. So who thinks that quantum gravity effects on black holes will be observed in the next 30 years? Could I have a show of hands, please?
Real black holes that doesn't include quantum simulation? What do you mean?
Okay, let's first say on real black holes, not including quantum simulations. Okay, and then if we include simulations. Okay, and who thinks that none of these things will be seen? Quantum gravity effects. Okay, all right. Well, that was not a large. Hopefully the turnout in November will be a little bit higher than what we just saw here. Okay, otherwise. All right, so it's exciting but also challenging with this kind of mixed audience. So I tried to make a talk that would be mostly accessible to everybody with a few new results for the experts. So let me know if something is confusing partway through. So in the first part, I want to talk about semi-classical gravity. And I want to tell you that that's qualitatively different from classical gravity. We have exotic things like traversable wormholes, which are not allowed classically, and they're allowed once we include quantum effects. These guys are hard to produce in the real world, but they're possible to study in quantum computers. And this more generally than traversable wormholes, there's perhaps a zoo of exotic solutions, which in my view is still uncharted. So this is an interesting open question. But I also want to talk about not just the semi-classical limit, but situations where non-perturbative quantum gravity effects could be important. And there, I want to claim that these non-perturbative effects in real black holes will be too small to observe. But they can be tested using holography in quantum computers. If there's time, I'm going to mention a fun result about how the long-time correlator, which is a probe of unitarity, is quite different in pure states than in mixed states. Okay. So for the first part, I want to talk about, yes?
But you can simulate a quantum computer with a large enough classical computer. So
fair enough. Fair enough. Okay. So what is semi-classical gravity? It's an approximation where we take the Einstein equations and we put in the expectation value of the stress tensor. This is not a good approximation in all states, but in some states, this is a good approximation. So you might think, oh, well, we're just putting in small quantum corrections. It's going to be qualitatively the same as classical gravity with small corrections. But that turns out not to be the case. It turns out that there's exotic objects of various kinds that can't exist in classical gravity. So we want to know, let's say, relevant to black hole observations, whether there can be exotic objects that look like black holes from the outside, but they're really not black holes at all, right? If those objects really existed, it would be very exciting to try to look for those things, okay? And this equation, of course, is not enough to answer that question because, as most of you know, any metric that you like, you can put it in there, you can compute the Einstein tensor, and it will solve the Einstein equations for some value of the stress tensor. Okay, so we'll come back to this question of what are the allowed stress tensors that you can have in semi-classical gravity. But first I want to start with a very concrete test case before we come to generalities, which is traversable wormholes. Okay, so I'm not actually sure there's a completely rigorous definition of a traversable wormhole. As far as I'm aware, the best definition is that it looks like a black hole from the outside, but there's no singularity. And in fact, an observer can just travel through this black hole and come out the other side into a distant part of space or perhaps into a different asymptotic region. Okay, so this is something that sounds like science fiction. And classically, it is. So classically, we have this null energy condition, which says that certain components of the stress energy tensor are positive, are non-negative. Roughly, it's the energy seen by an observer moving at high speed that always has to be non-negative. And all sensible classical theories satisfy this condition. And this combined with the Ray-Chuduri equation, which follows from the Einstein equation, basically tells you that matter has to focus light rays, and it can't defocus light rays. And so if we go back, you can kind of see that these light rays that come through this traversable wormhole, they first get focused as they go down into the thing that looks like it will be a black hole, and then they have to defocus. That's not allowed when you obey the null energy condition. And so this leads to beautiful things like the Penrose singularity theorem that tells you that a trap surface leads to a singularity. Okay, so classically, nothing crazy can happen. Okay, bouncing cosmologies can't happen, traversable wormholes can't happen, and any kind of exotic things that look like black holes from the outside are very strongly constrained. Okay, now what about when we add quantum corrections? We go to semi-classical gravity. Well, then this null energy condition turns out not to be true anymore, and we have various exotic solutions that are possible. And perhaps the simplest one to talk about is a traversable wormhole that's just built in the standard model plus general relativity. Okay, so this is a picture I took from a talk by Juan Maldacena. But this picture was actually drawn by Wheeler in 1966. I don't know what he was thinking when he was drawing that picture. But this was turned by Maldacena and collaborators into a self-consistent, rigorous solution of the standard model plus general relativity. So what this looks like from the outside is two magnetically charged black holes. But instead of having a singularity inside, you can actually travel through this Einstein-Rosen bridge and come out the other side. So this can exist in the real world, at least if the theory up to suitable energy scales is just given by the standard model plus general relativity, which could be the case. It's not clear if those are actually produced. So there's no obvious mechanism for producing those things. It's not clear that we could produce them starting from separated black holes. That would probably take a very long time. And if they did exist, they would be very small. So their separation needs to be smaller than the Compton wavelength of the electron. Okay, so these exotic things, they can exist, but unless one of the things I've said here is wrong, it's unlikely that we're going to be able to observe those things. Okay, that's not fully established. We don't know what kind of dynamics happened in the early universe. Okay, and there's some brief speculations in this paper about how they could have been produced. But that's a bit of a long shot. So if we're not going to see these kind of things in real life, we do have another possibility, which is to try to see these things using holography. Okay, so there we're not looking for black holes in the real world. We're making use of the ADS-CFT correspondence in order to probe these things in quantum computers or in the lab. Okay, so there's various examples, and in fact, the first, in my view, legitimate traversable wormhole was constructed by Gao, Jafferis, and Wall in this ADS context. Our contribution was a black hole which asymptotically lives in four-dimensional anti-de Sitter space-time. It's very similar to this black hole constructed by Maldacena and collaborators. But by putting in ADS4, you get some additional control, and you have the opportunity to try to examine this thing in a quantum computer. And a particularly nice thing is that these things are constructed in a simple way. You take two copies of a holographic conformal field theory, and you just need to couple them. There's two kind of constants that appear in this construction. One is a chemical potential type term, this mu. And the second one is this coupling between the two CFTs. Okay, so you just have a single operator that you need to couple between the two sides, which from the bulk point of view corresponds to some charged fermions. And what we showed is that the ground state of this relatively simple system is dual to this traversable wormhole that I showed on the previous slide. Okay, and so this gives you a simple way of preparing a traversable wormhole. And so you can simulate this in your quantum computer, or if you're lucky enough to have access to a holographic CFT in your lab, then you can do this in your lab.
What does dual mean here? Dual. What does that mean here? What is this?
Well, so we're working within the ADS-CFT correspondence, so every state has a description in the CFT and also from the bulk point of view. So all I meant is that I could have just said the ground state is a traversable wormhole in the gravity description.
Some way to construct the traversable wormhole out of the data of this ground state?
Yeah, you can see the data. You can see what the metric is. Yeah. Okay, so just to kind of summarize the traversable wormholes. So just over the past decade, these have moved from science fiction to science. Finding them in the real world is a long shot, but simulating them in quantum computers can be done. And in fact, well, there's been some controversy in this field, but some progress has been made in those directions. And so I think from this point of view, you would say that at least in the 2D construction that was simulated here, quantum gravity in 2D has been observed. Okay, but let's go a little more generally than traversable wormholes, okay? Because what one of our jobs, I think, is we should be able to tell people who are doing all of this hard work that we saw in the previous talk, should you be looking for something that is not a black hole there, okay? So we should be able to say more generally, what are the constraints within semi-classical gravity? And the obvious strategy is to constrain the negative energy that we can have in quantum field theory, and then use that to constrain geometry by using the Einstein equation, just like Penrose did classically. So for that, we need some bounds on the negative energy in quantum field theory. And this is also just a very simple, robust question in quantum field theory. What sort of bounds are there on how negative the energy can be? Okay? So we have some beautiful energy conditions that have been proven in quantum field theory that I don't have time to describe in detail. We have this average null energy condition, this quantum null energy condition. But I'm not fully satisfied with those things because they either involve an integral over an infinite amount of space, or they involve a bound that involves a state-dependent quantity, a derivative of the entanglement entropy. But what I would like to have, and what it seems like should what seems like should exist, is a state-independent, somewhat local bound. That would be the obvious thing to put in to prove a Penrose-type theorem in semi-classical gravity. Okay, so, and even if you don't care about gravity, this is a simple quantum field theory question. Is there some kind of bound on negative energy in quantum field theory? So this is something that I've been looking at with some collaborators over the last few years. Now, the most obvious thing is to just look at the expectation value of the null energy at some point. But that's known that that can be arbitrarily negative in some states. So what you need to do in order to get a bound, also what's physically relevant for back reacting on geometry, is you need to average over some region of space-time. Okay, and sometimes that's called smearing in this context. And the type of thing that we've established in particular examples is kind of an uncertainty principle type bound. Okay, so you're probably familiar with, in quantum mechanics, you have this energy-time uncertainty principle, right? Over short amounts of time, the energy can be somewhat uncertain. And what we developed is kind of a null energy space-time uncertainty principle in quantum field theory. Okay, so if we look in 3+1 dimensions, we take the null energy and we average it over some space-time region. So we average it over some region, some distance in space and some amount of time. Then we can get this simple kind of bound, which says that the null energy average over that region is bounded by a certain negative number. Okay, what we really had to prove is that the bound was not minus infinity, because once you know that there's a finite bound, then symmetries and dimensional analysis basically tell you that it has to take this type of form. Okay, so you can either think in terms of the length and the time, or you can think in terms of the two null coordinates that you're smearing over, that you can call delta x plus and delta x minus. Okay, so you get this simple kind of uncertainty type of bound, right? So you can see that this tells you if you average over a larger region, then the average null energy over that region has to become closer to zero, right? So if you want to have negative, you can have a lot of negative energy in a small region, or you can have a little bit of negative energy in a larger region, and this constrains building things like traversable wormholes. So we proved this, and some students in Amsterdam proved this for fermions. But really so we call this double smeared null energy condition. But we proved this in a very restricted context of free fields in Minkowski space-time. Okay, so then this thing n is just the number of fields. So, well, you could, if you're optimistic, say this is a hint of a general result. It seems quite sensible. But on the other hand, it could just be an artifact of free theories. Okay, so I think that's a very important open question. If this is correct, then it's basically telling you can't have isolated negative energy, and negative energy needs to have some positive energy nearby. Okay, so this is an area where you don't have to solve quantum gravity. You just have to answer in quantum field theory, or maybe even just in the standard model, what are the kind of limitations on negative energy in some region of space-time? Okay, and in fact, there's no known result, except in these free theories, above 1+1 dimensions. Okay, so in 2D CFTs, there's plenty of everything is understood, but above 2D, we don't know anything, even in perturbative interacting theories. Okay. And recently I've been somewhat paranoid because of some examples that this is just an artifact of free theories. And so I've been just looking for any case where we can prove this more generally. So I've been looking at CFTs in larger than 2 dimensions, but that's not really my native area of expertise, so it's been somewhat slow. So if you have suggestions for counterexamples or how to prove this, then I would be very happy to discuss. Kind of Another thing that's needed in this approach is once you have some kind of energy condition in quantum field theory, what does that tell you then for the allowed geometries? Okay, so you need to say how you need to develop some type of modified singularity theorem that adapted to the type of energy conditions we have in quantum field theory. Okay, so that's, let me come now briefly to some non-perturbative effects. So these things I've been discussing so far, they're exotic and exciting. A lot of stuff is not known. But, you know, you guys have these great string theorists in this collaboration, and you don't need them for this. Okay, it's just perturbative. You just need gravity EFT. Okay, in fact, you should probably hire some different people if you want people to do that, really, you know. But what would be great, though, and what, of course, I would really like to do is to test, like, the hard part of quantum gravity, the non-perturbative effects. So let's ask about testing those things, okay? So, of course, naively, strong quantum gravity happens only at the Planck scale, but the black hole information problem told us that some non-perturbative effects have to extend to larger length scales, and in particular, the Hawking radiation has to contain information about the microstate of the black hole. So there's definitely large non-perturbative corrections to the entanglement entropy. But it would be very nice to know whether there could be observable corrections to observable quantities, right? We can't observe the entanglement entropy. I'm going to assume that observable quantities means like correlators of simple operators, right? Now, in some models of how the information gets out of the black hole, such as the nonviolent unitarization model of Giddings, the answer is yes. So 2-point functions of gravitational perturbations near black holes are modified at order 1. I think conservative view is that these things are very small. And in some versions of fuzzballs, these things are quite modified, and in some other versions, they're not. So we developed some technology to look at this. So what we consider is, suppose you have some ensemble of pure states. You should think about, you know, different microstates of a given black hole. We examined a weird quantity called the quantum deviation, which is basically telling you, like, how much does the expectation value vary over this ensemble of pure states. So this weird overbar is indicating the ensemble average over an ensemble of pure states. Okay? And what we showed, this is just a quantum mechanics result, which I presume somebody else has derived before, is that in these a suitably defined ensemble, the variation of this thing is exponentially small in the entropy. Okay? So when you take a typical pure state, the expectation value is exponentially close to the average over the ensemble. Okay? What this is, in detail, this is saying that it's related to actually a correlator in a doubled system, in this thermal field double state. So in a recent paper, we translated this into a bulk statement. So let's look at the correlator near the black hole. And this quantity is simply telling us, is that correlator sensitive to the microstate of the black hole? Okay? That's diagnosing the size of quantum gravity effects. Okay? And sadly, there's this e to the minus s sitting here. Okay? So this is quantitative support for this conservative view that the non-perturbative effects are very small unobservable quantities near the black hole. Okay? The effect does grow when you look at higher point functions. Okay? It's consistent with S-point functions having order 1 corrections. But this would give a strong constraint on scenarios like nonviolent unitarization in some versions of fuzzballs. So it's very important to ask whether there's some loopholes in this result. Let me skip over this because I'm kind of out of time. A kind of fun thing is that the long-time correlators behave quite differently. They're much larger in pure states, and they have a much more regular time dependence. Okay, so let me finally come again to how could we test these non-perturbative effects. So one concrete proposal we made, if we come back to these traversable wormholes in ADS, as you dial these two couplings that I was telling you about, you go from a situation where the ground state is a disconnected geometry to a ground state where the ground state is a traversable wormhole. There's a non-perturbative process where you can transition between those two things, given by a gravitational instanton, and we computed the rate for that thing. Okay, that's topology change, so that can only happen due to a non-perturbative effect. And that's something that, in principle, you could compare to a simulation of this system. Okay, so let me summarize. So crazy things can happen in semi-classical gravity. There's many open questions there. Sadly, I claim that the non-perturbative corrections to observable quantities near black holes are exponentially small in the entropy. But we can test these non-perturbative effects using holography. And then there's some important open questions, figuring out what type of exotic objects we can have in semi-classical gravity. For that, we're going to need some energy conditions in quantum field theory. And we can look at testing these non-perturbative effects using holography. I want to mention one more thing, because I'm hoping to get some feedback about this. So one thing which I think has not been computed is simply the quantum fluctuations, just the perturbative quantum fluctuations of the black hole horizon. Okay, so it's a very basic thing in quantum gravity, right? How big is the fluctuations of the horizon? So there's a paper by Merrill from 20 years ago where he gives an estimate which has an interesting length scale, right? Which says that there's a quantum width in the black hole horizon, which is the geometric mean between the Planck scale and the Schwarzschild radius. There's some recent papers saying that this calculation is wrong. But there's a derivation of this same distance scale, claiming that this is where effective field theory breaks down, with completely different reasoning in this recent paper by Busso and Pennington. And in fact, the distance scale is the same one in all dimensions, okay, not just in 4 dimensions, which is what I'm writing down here. But as far as I'm aware, no one has computed the very simple perturbative GR question: what is the size of the fluctuations in the black hole horizon? And it would be very interesting if it's a large distance scale like this one. Okay? But do please let me know if you know something about that, because I'm anticipating a very painful question about how to fix gauge properly in this thing, how to define the horizon when it's fluctuating and so on. So I look forward to discussing with you guys over the next couple of days.
All right, thank you, Ben. I already see many questions, so I saw that one first, if Nicole can get to it, and then we'll go here and make our way around.
Hi. So you said like you want to measure this deviation in a simulation. And Andy's comment notwithstanding, you probably mean quantum simulation. What do you actually want to measure? I mean, can you say a bit more, please?
Well, one thing, so you have this topology changing process, and that's the obvious thing to try to look for. I haven't thought in detail about the best way to do that, but so you need to think about how the correlators between those, or you need to send a signal and see whether it goes through to the other side.
But I mean, if you go to your colleague who has a quantum computer, you have to tell them what to measure. So what's the actual quantity? I mean,
fair enough. Yeah, no, I have not. I have not defined that in detail yet. I think that's an important thing to do. Yeah.
Thanks.
Okay, now we'll come here.
I was actually going to ask about your black hole horizon fluctuation. Isn't that a gauge-dependent question? So maybe I'll rephrase. How do you define in a gauge-independent way? What do you mean by the fluctuations of the black hole horizon?
No, that's a good point, and I have not started calculating yet. But you know, it seems to me that there's some physics question. There's some sense in which if you're very close to the horizon and you send a light ray, there's probably some region where the probability to get to infinity is order 1, and the probability to fall in is also order 1. Right? So I think that there should be some definition. It's not clear to me yet. The unique way of how uniquely defined that is. So probably you should think. I probably have to think more carefully about like what observable you want to look. That probably requires introducing a probe of some kind.
All right, maybe one last quick question. Perfect.
I was very struck by your remark that quantum gravity is observed or understood in 2 dimensions. Now, I know that people like de Hooft have argued that actually, when you go towards the quantum gravity situation, you do actually go to a 1 + 1, a 2-dimensional description of the world. Is this the same argument, or is it a completely independent argument which would relate to that?
As far as I know, this is a completely independent argument, and it's just because these people doing quantum simulations were limited to simulating quantum mechanics rather than quantum field theory.
Well, he did have some physical reasons for why it was going to 1 + 1, and I just wondered if that was the case, can you then apply your argument to?
Yeah, possibly, but I'm not aware of that. These people have not made use of these people have made use of JT gravity and the dual with the SYK model, and I'm not aware of that following from the 't Hooft reasoning.
Okay, thanks.
All right, I think the rest of the questions will have to wait for the immediate coffee break. So let's give another round of applause to Ben. Thank you.
All right. So I hope everyone is back here from the coffee break. It's my pleasure to welcome everyone here in our last session of the day. I'll be chairing it. I'm Sasha Plavin, a postdoctoral fellow at the BHI. In this session, we have 2 talks, and the first one, the first one will be by Dennis Overbye. He is a correspondent for New York Times and science writer in physics and cosmology, astronomy. And he will be talking about some similarities between cats and black holes. And let's enjoy the talk.
Oh, thank you. All right. Well, despite my terror-stricken demeanor, I'm very excited and honored to be here today. Pretty much everything I think I know about black holes I've learned from people in this room or their mentors or maybe their competitors. I don't have too much to add to that. So my job is to provide a little comic relief and tell you what this has all looked like from the bleachers where I sit. I want to apologize in advance for too many metaphors and not enough slides. So, all right. There's the New York Times, where I've worked for the last quarter century. I have the privilege of walking around with one of the most, coolest and pretentious business cards in journalism. People ask how I got that title, and the answer is that I was lucky. So I can trace my science writing career back to a single day in December of 1976 when I saw Stephen Hawking roll down the aisle of the Copley Plaza Hotel just across the river in Boston. It was the second day of the Texas Symposium that year. At the time, I was an assistant typesetter at Sky and Telescope and a failed novelist. I had heard a little bit about Hawking, but didn't really know much. And of course, he was there to talk about exploding black holes, which sounded pretty interesting. But there was something mythic about the whir of his wheelchair, the sudden silence in the room as he proceeded down to the front. It was one of the most dramatic scenes I thought I'd ever experienced. To me, he was St. George approaching the black hole dragon. I ran up to the aisle to help him because we had to lift his wheelchair onto the stage. Oh, yeah, there he is. There's the dragon, anyway. I'm not clever enough to get Hawking into the picture. So as soon as I could, I hopped a plane to England and spent a week following him around, much to his dismay. I wanted to write a book about him, but he turned it down. So I didn't know then that I would eventually write his obituary for the New York Times. So I had long ago drunk the Kool-Aid about black holes. John Wheeler had me at hello. I thought it was too cool to contemplate that the laws of physics actually had the end of physics encoded in them. And I've been following that dark star ever since. This is from a trip with an early observing run with the EHT. So it's a pretty natural obsession, I think. You don't have to be a deep thinker to realize that black holes might inspire a connection with human psychology. Well, there's the black hole of Calcutta. There's Jonah about to be swallowed by a whale. There he is in the whale. I just picked this up. There's Kali, the personification of creation and destruction. And there's Kali with Mick Jagger's tongue. Joseph Campbell called her the terrible one of many names, whose stomach is a void and so can never be filled, whose womb is giving birth forever to all things. I read that passage to Stephen when I was visiting him in Cambridge. And he said it was fashionable rubbish, and he rolled off over my toes. But I've persisted tagging along with astronomers and theorists and trying to understand what physics has been up to in the last half century and what it means. And I've gone through various stages of, first comes denial. So maybe there's the canonical gravitational collapse. Maybe the singularity doesn't exist. So George McFitty, who was a well-known radio astronomer, had not drunk the Kool-Aid back in 1970 when this picture was taken that went with my first article about Hawking. Neither did Einstein. In 1939, the same year that Oppenheimer published his paper predicting the massive black holes could collapse forever, Einstein wrote a paper purporting to show that black holes couldn't exist. As a teenager, I was a fan of the steady state theory, and so I was sympathetic to these doubts. And I tested it out one pharmaceutically advantaged evening, lying on my back in the grass, looking up, trying to imagine a universe without a beginning, but it didn't work for me for various reasons. And it turned out we were all wrong. And Hawking and Penrose by then had already shown that, in fact, nature was that strange and cruel. And the monsters were beginning to show up in the real world. There's Cygnus X1, X-ray observatories like Uhuru were spotting invisible things eating gas and spouting X-rays. Mighty wheels, houses of energy, were powering quasars and radio galaxies. There's our pal M87. Space was speckled with things we couldn't see. There seemed to be monstrous sucking pits in the centers of most galaxies. And possibly tiny primordial black holes and virtual black holes could be eating space-time out from under our windows and spitting out chaos. Death roamed both inner and outer space in popular culture. There's Jerry Garcia with the Dark Star, became their sort of their signature piece, never played the same way twice. Oh, yeah, there's a famous Disney movie. I guess this was the more recent sequel to the Disney movie, right? There's Gargantua. Kip Thorne's black hole, which was done so well that he wound up writing papers about it. And there's, of course, the EHT black hole. Sort of looks the same. There it is. And I don't know whether that's going clockwise or counterclockwise either, but I like the sort of the grooved shape. Changed. Stephen Hawking released us from all that doom when he locked himself in a bathroom 50 years ago and finally concluded, to his eternal surprise, that black holes were not black, nor were they eternal vaults. They were hot. And your mass energy could come back. See, there's Jonah getting spouted out onto the beach. But there was a problem, of course, because Jonah came back without his wits and didn't even know his name. He didn't have a history. Black holes were going to erase all that information. And Hawking, in his speech in the Copley Plaza, said, God not only plays dice, he throws them where he can't be seen, which I thought was very cool. Why not? I liked the idea of the universe eating, slowly forgetting itself, but some people didn't. There's all the ones and zeros disappearing into a black hole. But I didn't know enough quantum mechanics to realize that this was a horrible slap on the face to the whole idea of science or physics. Energy had to be conserved in order for the universe to make sense, or at least so they say. There was a big famous debate that ensued. A bet, yeah. Hawking was a betting guy. So I remember Lenny Susskind at Hawking's 60th birthday party, where he said, Stephen Hawking is one of the most obstinate people in the world. No, he is the most infuriating person in the universe. Well, Hawking was grinning in the back row where I was sitting. So, of course, 2 years later, Hawking conceded, but he probably conceded too soon because nobody had yet figured out how information actually did get out of a black hole. And of course, this led to the firewall. And the double bind, you couldn't get into a black hole, and you couldn't get out either, so you're stuck. Meanwhile, a great plague descended on the earth. I wrote one article about it, about how it might affect the experiments at Grand Sasso and generally about physics in general. Meanwhile, my colleagues on the science desk were going to war, and they were all becoming experts in virology and epidemiology and vaccines and ventilators. Actually, half the physicists that I talked to when I wrote this article were like busy inventing ventilators, which it turned out when I talked to an actual doctor who used these things, he said he wouldn't touch it with a 10-foot pole. But so I wanted to join in, but my editors said, never mind. Keep writing about black holes, they said. We need some comic relief from COVID and Trump. So I was happy to oblige. And so were the readers. They loved it. I kept getting letters saying, thank God we're not, it's just not all about us. So black holes did become the cat videos of astronomy. And I'm not going to talk about all these different stories. I asked Ed Witten what he was doing during the pandemic, and he said he was investigating whether Planet 9, which we still haven't found, could be a black hole. It was news to me. Black holes were news if they were there, and they were news if they weren't there. Cygnus X1 got bigger. On and on. More black holes, more black holes. So this was sort of fun, because found out these astronomers at Vanderbilt were trying to decide what they should call a bunch of black holes. And so I wrote about it, and we had a contest, and people wrote back in words like sieve or cauldron or colander came up. I decided that they should be, a bunch of black holes should be called a litter, because they're fun from a distance. Anyway, so, yeah, all right, so meanwhile, theorists were busy rebuilding black holes from the inside out, and what emerged, this idea is that we live in black holes are holograms, and we live in a holographic universe. This is the second time this image has been showed today, and everything that happened inside this tin can was related to basically the labels on the outside. So this feels to me like Plato's cave. We're watching shadows and mistaking them for reality. And, it's kind of a grim existence. And it leads to the question, like, are we For some reason, this reminds me of the black hole of Calcutta. I don't know why, but right. Selenia Susskind once told me, we don't read the hologram, we are the hologram. There's another idea I thought was cool, but it leads me to wonder whether we are here at all or we're just shadows. Are we controlled by the Matrix? Is this just a big video game? What puppets were dancing on black hole, on wormhole strings? I'm not quite sure what this is. I just think it's very cool. Maybe somebody can tell me afterwards. So the question, and some people think that maybe social media is the new Plato's cave, maybe. But I have to leave that to other people to decide. And the question is, can we get out of Plato's cave? So it may be that we already are out of Plato's cave, so the new idea of black holes is that the inside is the same as the outside. They're connected by all these wormholes. Which leads me to believe that, well, a black hole is just a Klein bottle. The inside is the same as the outside. However, well, recently I heard my neighbor Jan 11, who's a cosmologist at Barnard, gave a talk, and she said, you shouldn't think about black holes as a thing. It's nothing. There's nothing there. So it's not a thing, just an artificial, archaeological artifact, a scar in space-time. Maybe this is the wildest, maybe a topological qubit in a cosmic computer. So what happens when these artifacts of nothingness collide, nothing on nothing? It produces the largest clap in the loudest clap in the universe. So that's of course my tribute to LIGO, and I can't play the chirp. I was going to mention just a few other people I'm grateful to for having given me something to write about all these years. That's EHT. There's Chandra, which is facing a dubious anniversary this fall. These guys need no introduction here. Oh, all right. And I can't play this either, but I think it's only going to get weirder. The chirps on my LIGO app are going off like every day now, often in the middle of the night, and so I fantasize that some of these chirps will wind up being things that we don't yet know about, other versions or formations of nothing. So thank you all for the ride and inviting me here, and I hope it never ends. So what can I say but thanks for nothing? I'm pretty sure I was going to... Oh, no, well, all right. That's not part of it. Okay, we're done.
All right. Thank you, Dennis, for the talk. So, any questions?
Oh, I have questions.
Any questions?
No.
Yeah, Peter.
Nobody wants to know why the New York Times is lying to them? Or... I get that sometimes.
Dennis, when you hear from the readers of the Times, is there an overall sense of what interests them about black holes? Why they find it exciting?
The leaders, yeah, they think it's cool. I mean, they give shout outs to these articles that I wouldn't have, because they're all political junkies, right? I mean, the people that run the New York Times, but I regularly hear from them. Yeah, so they think it's cool. I mean, they let me get away with calling myself the cosmic affairs correspondent for 20 years. I mean, I was a little worried about that at first, but I think it's fun. Yeah, Andy.
Of course, you cover many different things in astronomy and science and physics. Are you somehow driven to write a lot about black holes by the public, by the editors, by your own interest?
I think it was my own interest, but they're happy to let me do it. I think everybody they strike a kind of a universal chord. Like, you know, I showed that picture of a grave, right? Everybody knows what that is. It's a lot harder to explain the Higgs boson or yeah.
So some of the fascination of black holes must be because we hadn't seen one or heard one before, so you can make a movie about something that you haven't seen or heard. Do you think, given the fact that we've seen and heard them now, that that's going to change literature or film going forward, because they'll have to incorporate things we actually know?
Well, I don't think so, because I mean, Interstellar was made before we ever saw or heard a black hole. No, I mean, they're still mythic in the minds of the public.
I want to ask you about a book that you wrote a book, Einstein in Love, right?
Yeah, yeah.
I wonder, did you interview people that were connected with Einstein or friends or did you base your book on some primary sources? I wonder how you wrote the book. I read it. Actually, I have it at home, and I enjoyed it.
Thank you.
So
you're the one.
That's what I wanted to ask you about this book. No, I'm an Einstein scholar, and I study Einstein. That's why I'm interested.
You know, it's hard to interview anybody who knew Einstein because they're all gone. But I did interview children and grandchildren of people who knew Einstein, and plus I read through all these thousands and thousands of letters that the Einstein Papers Project had collected, and you know, some that they hadn't collected yet. I mean, does that answer the question? I went every place he ever lived. I mean, it was a fun book to research. I got to spend a lot of time in, you know, cool places in Europe.
Hello, thank you very much. You also wrote another book called The Lonely Hearts of the Cosmos, and I was wondering if you see whether the cosmos has become less lonely more recently. Have we less lonely hearts in the cosmos, or does cosmology still consist of a lot of lonely hearts?
Good question. Well, of course, I mean, several of the lonely hearts that I portrayed in that book are gone, like Alan Sandage and John Wheeler, Stephen Hawking. But I think the I mean, I think the cosmos is still lonely. I mean, we still don't have any company. And of course, maybe I was the ultimate lonely heart of the cosmos. But thank you for asking that.
Thanks. So we may have time for just one quick question, if anyone wants to ask the last one.
So, reading your pieces, I think one of the things that makes you a little different from most science writers is that you seem to have zero interest in the spin-off argument for funding science, that all the great technology we're going to get, from the science we do, which is often emphasized by a lot of science writing and policymakers and so on, and by us when we ask for funding. So I'm just curious if that's like a deliberate decision on your part. Well, first, if you agree, and if so, is it a deliberate decision on your part? And what is the reason for really focusing on the curiosity-driven part of the science
rather than technological?
Yeah.
I think it's partly just a personal taste, and partly because also, I mean, a lot of our technology coverage comes from the business department, and that, they have correspondence in Silicon Valley and so forth. But there's a lot that, there's a lot that doesn't get covered because we just don't have enough people to do it all.
Yeah. So I think we need to thank Dennis and...
Well, let him ask.
Yeah, let's try.
Daniel.
For a quick question.
So I was just curious, so you've been writing about black holes for many years, saying what the experts say, and we keep changing our story. You lose information, you don't lose information, there's a firewall, there's not a firewall, I mean, does that, I don't know, do you take us seriously? Do the readers take us seriously?
Seriously
yeah,
what you...
I don't know. I mean, yeah, you asked 5 different people in the room a question, you got 5 different answers. I don't know.
Well, that's what makes it fun. I mean, there are no final answers, right? It's just like this endless, it's a human effort, right? So of course, people are going to be wrong and change their minds. Otherwise, it would be boring.
We have one more quick question. Thanks. Hi, Dennis. So you have had amazing relationships with some of the, pioneers in our field. And I was wondering if there was something that you think we should know about them, that you discussed or discovered about them throughout their lives, something that might surprise us or interest us.
Well, who are you referring to exactly?
Whoever you, I mean, you've known so many of the giants. Whatever comes to mind is totally fine.
There are no giants, only people.
Well, that's true, but I think what comes...
Wheeler or Hawking are the two that come to mind, but maybe there's something surprising about someone else.
I think what comes to mind to me is how deep and disciplined their knowledge about physics is. That they've really done their homework and know their stuff. It's not just all kind of flashy quotes, Wheeler's famous for all his aphorisms, right? And Hawking is just famous for being Hawking, but they all really worked hard and knew their stuff. I'll make an inappropriate comparison here because I've been a lifelong fan of Bob Dylan. And the more I know about him, the more I realize how he really did his homework in music long ago. I mean, he really knows his stuff. It's not just he just started one day popping up, composing these amazing lyrics. I mean, he was like, it goes way back for him. For probably anybody who's succeeded at their art and their science, there's a lot of invisible background that isn't immediately apparent until you start digging. So maybe that, I don't know if that suffices. Of course, I like it when they let their hair down and engage in wild metaphors.
All right, let's thank Dennis again. And we welcome in our second speaker for the session and the last speaker for today, Bernard Carr. He is a professor of mathematics and astronomy in Queen Mary University in London, and I hope everything will work fine. And we will be hearing about the vast scales that black holes cover, from Planck scales to Hubble scales. So the floor is yours.
Thank you. It's a great pleasure to be here. Dennis, you started your talk by saying you had too many metaphors and not enough slides. Actually, you had beautiful slides. I probably got too many slides and not enough metaphors, but I'll do my best. My title is The Pervasive Black Hole from the Planck Scale to the Hubble Scale. And what I want to do is I want to stress the huge range of masses over which black holes could exist, even though most people only focus on a rather narrow range of masses. In particular, I'm going to talk about primordial black holes, that's PBH, the black holes which form in the early universe. I think John referred to them in his talk, because that's a subject I've worked on for 50 years. And I'll try to persuade you they may exist. I have to be honest and say the very first article I ever wrote when I just begun my PhD was an article for the New Scientist, a popular magazine, a science magazine, called The Pervasive Black Hole. And so I sort of thought it would be funny to use the same title. But of course, the subject has evolved in the last 50 years. Now, first of all, I just want to remind you there is overwhelming evidence for stellar black holes, the results of stellar collapse in the range, say, 10 to 100 solar masses. Cygnus X1, of course, was discovered by X-rays in actually 1973. That's what triggered my first article. We know, of course, we had direct evidence from the LIGO detection of merging black holes, for which, of course, we got the Nobel Prize. Even last week, there was a report, the first proof of black holes plunging, the plunging regions where the matter falls into a black hole. So the subject is constantly evolving. So we know these black holes exist. We know, of course, there's overwhelming evidence for supermassive black holes. We've heard about that this morning. We've heard about Sagittarius A, and of course, there was the Nobel Prize for that, 4 million solar masses. We've heard today about the M87 from the Event Horizon Project, and indeed Sagittarius A as well. We now know that most quasars are powered by supermassive black holes, maybe in the range around 100 million solar masses, but some of the black holes are even bigger than this, and I think the maximum mass at the moment is 10^618, which goes up to 20 billion solar masses. And I have to say, I've always been fascinated in the, recently been interested in the possibility that there could be black holes even larger than that, bigger than 10 to the 12th, which we christen slabs, stupendously large black holes. But I have to say that the credit for this idea really goes back to Priya Natarajan, who wrote a book on essentially, not a book, a paper on the same topic many years before. But it was embarrassed to find I hadn't read Pear's paper when we produced this, but we were able to add a reference. And of course, recently we've had possible evidence for binary black holes from the Nanograv project, where they're detecting gravitational waves using pulsar timing arrays, which is in the frequency range which would correspond to emerging binaries, supermassive binaries. Now, intermediate mass black holes, they're the ones between, say, 1,000 and 10 to the 5th solar masses. The evidence for them is not quite so convincing, but there are good arguments, I think. There are particular sources. There's an X-ray source which might have a 500 solar mass black hole in it. That's what's called another source which might have a 2,000 solar mass black hole. And there's a globular cluster called Omega Cen, which might have a 4,000 solar mass black hole. I don't have time to go into the evidence, but as I think John Mather mentioned this morning, it's possible that the first population of 3 stars may have been in this mass range. But now what I want to talk about is primordial black holes, which is my own research interest. As you know, a black hole has a radius proportional to its mass, so the density required to make a black hole goes like 1 over m squared. So the smaller the black hole, the more density which is required to form it. You can't form a black hole less than the mass of the sun in the present epoch. But when you go back to the early universe, the density becomes arbitrarily high. It goes like 1 over time squared, t being the time from the Big Bang. And so comparing the density at the top, rho s, with the density of the universe tells you immediately that the black holes that form at a time t have to have what is essentially the horizon mass, the mass within the distance traveled by light, which is just given by that formula. So you can see that if they formed at the Planck time, 10 to the minus 43 seconds, they would have the Planck mass, 10 to the minus 5 grams. If they formed, though, for example, at 10 seconds, when the electrons and positrons annihilate, they would have 10 to the 6 solar masses. So primordial black holes could have a huge range of masses, which is what makes them interesting. The ones which form at 10 to the minus 23 seconds, they're the ones that would have a mass of about 10 to the 15 grams, and we'll see why those are very important because of Hawking's result. Now, I don't have time to go into a detailed description of why they form. Just because the universe has a high density at early times doesn't mean that you have to form black holes. You need to have some form of inhomogeneities. But there are different ways in which they could form. The most natural one is to say that you've got large density perturbations, which would have been generated by inflation, and then in certain circumstances they produce black holes. Alternatively, you can have a reduction of the pressure. For example, you get a reduction of the pressure at the QCD epoch at about 10 to the minus 5 seconds. And then they could form more easily. You can have cosmic defects. You can form cosmic strings, which form cosmic loops and then collapse. And there is a certain probability that they will form a primordial black hole. You could have a phase transition, which produces bubbles of broken symmetry, which then collide. And the collisions can produce primordial black holes. You can even have the collapse of domain walls or bubbles of broken symmetry. So there are a lot of ways of forming primordial black holes. That doesn't mean to say they do form, but it's a possibility. I don't know what the bottom... Sorry, something's gone wrong with this slide. Stephen Hawking wrote the first paper in 1971 about primordial black holes. He was the first person to realize that you could form black holes with a horizon mass, and he postulated that there could be black holes of the Planck mass, which actually form, and he assumed they would have charge, that they would capture electrons and form atoms, and those atoms would then, they would be detected in bubble chambers, and they might also collect in the middle of the sun, and explain the solar neutrino problem and things like that. Actually, that particular model turned out to be wrong because they don't preserve their charge. But nevertheless, this was the first paper which was postulating that primordial black holes could actually form. Now, I'm sorry, but something has gone wrong with the slides here. Something has gone wrong with the John. Something's gone wrong with the slides. They haven't come out in the right format. Sorry, can I just see how far serious this is? Okay, I will just carry on anyway. The formatting of the slides has come out all wrong. So let me just explain. I don't think we can do much about it because the formatting of the slide. Let me just say here, something is wrong about the size of the slides. I don't know what's gone wrong. In fact, earlier on, Zeldovich and Novikov, John, something has gone wrong with the slides. The size of the slides doesn't match for some reason. Never mind. I don't know how. I'll just have to go through it and see how it works out. In fact, Zeldovich and Novikov had argued in 1967 that there couldn't be any primordial black holes because they argued that they would accrete catastrophically and they would grow at the same rate as the horizon, and therefore they would grow to something like 10 to the 15 solar masses, which is that such black holes cannot exist. And that more or less implied that there could not be any primordial black holes. So the first project I worked on was with Stephen Hawking for my PhD, and we were able to show that primordial black holes would not accrete at all. And that was an important result because it meant that you could then start thinking about their properties. And there was no observational evidence against their existence. And I have to say that this was the first paper I ever wrote. And it's, in fact, my most cited paper. And therefore, in some sense, I always say my career has been downhill from the start. Because, but nevertheless, in a certain sense, it was very important because that meant people started thinking about the properties of primordial black holes. Now, as we know, Stephen Hawking in 1974, he discovered that black holes radiate and eventually explode, and we've heard a lot about this result. And they also have an entropy, which is just a quarter of their area. Now, and there's the famous expression for the temperature. It's very, very small for a solar mass black hole. It's just about 10 to the minus 7 degrees. But what was so conceptually important about this result is that it combined quantum mechanics and general relativity and thermodynamics. And although there is still no evidence for the Hawking effect, it's such a beautiful result that nearly everybody accepts that it must be correct. And it shows that actually PBHs are important even if they never form, because it was only as a result of thinking about the properties of primordial black holes that Stephen realized that the small ones would have these quantum effects. So I think this illustrates a general point in physics, that it can be useful to think about things even if they don't exist, because you get important physical insights. But as we said, we still don't actually have any definite evidence for primordial black holes. There was also the famous black hole information paradox, which we heard about earlier this afternoon. And don't try and read the abstract. Hawking inferred that there must be a loss of information. That was very controversial because it went against the principles of quantum mechanics. And really, Stephen, of course, changed his mind. He eventually accepted that he was wrong. And even 40 years later, we still don't fully understand this, but shortly before his death, with Malcolm Perry and Andrew Strominger, he was working on the resolution of this problem. And so, although this was a mistake, it was a very important mistake. And I think in physics, wrong ideas are often almost more useful than good ideas. I like this quote from Wilczek: an ordinary mistake is one that leads to a dead end, while a profound mistake is one that leads to progress. Anyone can make an ordinary mistake, but it takes a genius to make a profound mistake. And I think one would count this as a profound mistake. Now, black holes radiate with a temperature that goes like 1 over the mass. They evaporate in a time scale that goes like the cube of the mass. So for a solar mass black hole, this is completely unimportant. But if you have a 10 to the 15 gram black hole, it's got the mass of a mountain, but it's about the size of a proton. Its lifetime is the age of the universe, and so it's exploding today. Now, of course, I was with Stephen in Caltech in 1975, and the key question was, could we see these black hole explosions? And unfortunately, it could, of course, only be important for primordial black holes. However, already we knew from the observations of the gamma ray background that they could only have a very small, the 10 to the 15 gram black holes could only have a low density, because most of their life they're sizzling away and producing 100 MeV gamma rays. And this meant that the density of the black holes in the units of the critical density had to be less than 10 to the minus 8. And that was bad news because it meant that you wouldn't be able to detect the explosions, at least with the standard model of particle physics. But it's interesting that black holes which are bigger than the planet, the Earth, 10 to the 26 grams, their temperature is actually going to be lower than the CMB. So I always say the quantum black holes are the ones which are smaller than the Earth, that's about a centimeter, because their temperature exceeds that of the cosmic microwave background. Otherwise, they would be accreting instead of radiating. Now, black holes as a probe of higher dimensions, we have had some references to this. Hawking's picture is modified if you have extra dimensions which are compactified on some scale. Naturally, those scales are compactified on the Planck scale, but nevertheless, you can have large dimensions. And in that case, you have what's called TeV quantum gravity and the possibility of generating black holes in accelerators. So far, there's no evidence for that. But the point is that the size of the black hole, its temperature, and the lifetime are changed. So in principle, what was exciting was that you would have a way of actually probing higher dimensions if they were ever detected in the, for example, the Large Hadron Collider. There's even a sense in which a whole universe could be a sort of black hole. This is very speculative, but it goes back to the idea that of Lee Smolin, that when you form a black hole, it could actually collapse and form a baby universe, in which case you might argue that our whole universe is derives from a black hole. Even more exotic suggestion in brain cosmology is that our universe corresponds to a brain moving through the fifth dimension of a bulk. And in this case, you can think of our universe as emerging from a five-dimensional Schwarzschild de Sitter black hole. But that's, again, very speculative. Now, I just want to put this together using my favorite image. This is the cosmic Ouroboros, which is the snake which swallows its tail. And it describes all the scales of structure in the universe. So you go from the top left at the Planck scale, you go anti-clockwise down to up to the top right, which is the scale of the universe. In other words, you're going from the Planck scale to the Hubble scale. And so there you've got human beings at the bottom and successively larger things as you go upwards to the right and successively smaller things as you go to the left. You can think of this as a sort of ruler. Every minute corresponds to a decade of scale. So there's 60 decades. And I love this diagram because it summarizes the triumph of physics. Now, what I want to do, though, is I want to put black holes into this picture because they have a scale which is just related to the mass, so I can put that in this figure. So there's the stellar black holes, the intermediate mass black holes, million solar mass black holes in the Milky Way, the 10 to the 9th solar mass black holes, maybe the 10 to the 12th solar mass black holes, and then the whole possibility, in some sense, the whole universe is a black hole. But now the primordial black holes, they are the ones forming in the Big Bang, they sort of occupy the left side of this diagram. So, for example, you've got terrestrial black holes, lunar black holes, the evaporating black holes are 10 to the 15 grams, the size of a proton, and the ones which are exploding today, they're like 10 to the 10th grams. And then the Planck mass black holes, the smallest ones, they're right up there at the top left. And so I like this diagram because it shows how black holes link the micro domain on the left to the macro domain on the right. Because most people studying black holes normally focus either on stellar black holes or on supermassive black holes. But because I'm rather obsessed with black holes, I like to think of them in every possible context, and I think this diagram represents that. Also, I told you that the divide between quantum and classical black holes corresponds to the bottom of the diagram, and higher dimensional ones come in at the top of the diagram. And so this motivates the title of my talk from the Planck scale to the Hubble scale, because that's precisely where the range of mass is covered by this diagram. But the question is, therefore, do these things exist? Because the stellar black holes and the supermassive black holes, they just correspond to the white segments. But the primordial black holes, in principle, cover this whole circle, the whole orange range. And so the question is, do they exist? Now, I always say nature would be cruel not to populate the whole Ouroboros, but of course that's not a very good argument. However, what is undoubtedly true is that there has been a huge surge of interest in primordial black holes. When myself and Stephen started working on primordial black holes 50 years ago, there were very few publications. There was obviously an increase of interest when Hawking discovered Hawking radiation. But in recent years, for reasons which I'll explain, there's been a huge surge in the number of papers on primordial black holes, as indicated by these blue and green regions. So now it's hundreds of papers coming out every year, or even thousands of papers on primordial black holes. And I have to say, from my point of view, this is a problem because I can't keep up with the literature. And since I've worked for 50 years on primordial black holes, I want them to exist. Otherwise, I've wasted a lot of my life. But it was much easier when nobody believed in them, because then I could actually keep up with the literature. So why they're useful? Well, the ones of the Planck mass, they probe quantum gravity. If they're less than the Planck mass, they probe the early universe. They're evaporating, but you can still see their consequences. If they're about 10 to the 15 grams, you're seeing the explosions, and they would be probing high energy physics. If they're bigger than 10 to the 15 grams, then they would be, in some sense, providing some form of, they could provide, for example, the dark matter. Now, I don't have time to go into details. I just want to make one point, which is the fraction of the universe collapsing into primordial black holes must be very, very tiny. The reason for this is if I take the ratio of the black hole density to the cosmic background radiation density, if the density of the black holes is omega PBH, then the CBR is about 10 to the minus 4. So at the moment, that ratio may be very large. But as you go back in time, the density of the black holes goes up like 1 over r cubed, where r is the scale factor of the universe. The density of the radiation goes like 1 over r to the 4th. So this ratio goes down. And so the fraction of the universe in black holes at the time they collapse, which is called beta, it would have been very, very tiny. Even at 1 second, for example, it goes like t to the half, but at 1 second it would be about 1 in a million. But of course that relates to the mass, as I showed before. So, for example, for a 10 to the 15 gram black hole, it would only be 10 to the minus 18, and that would be even if omega PBH was 1. So you require the collapse fraction to be tiny. And this is one reason people sometimes think that it would require too much fine-tuning. However, it's also true that you expect the collapse fraction to be very tiny, because the collapse fraction depends on the amplitude of the fluctuations in the early universe at the horizon epoch. We know to make a black hole that has to be very large, close to 1, but we know from the CMB that it has to be very small. on the CMB scale, the fluctuation amplitude is only about 10 to the minus 5. Now, we've heard a lot about inflation, or at least cosmologists think a lot of time thinking about inflation. The first thing inflation does is inflates away primordial black holes which formed before inflation. So there wouldn't be any more left, say, bigger than, which were smaller than 1 gram. But also inflation generates perturbations. You scale down, you have your scalar field which is rolling down a potential, and that generates perturbations. And so the question is, can the PBH, can those fluctuations generate the PBHs? There's a huge number of papers on this. If you have a model of inflation, the first thing you do is check whether it makes too many PBHs. Now, the question which most interests people is whether black holes could make the dark matter. That's to say, could the black holes bigger than 10 to the 15 grams provide the dark matter? And the reason for that is we know from cosmological nucleosynthesis that the baryonic density must be about 0.05 in units of the critical value, whereas the dark matter density is something like 0.25. So you need some form of non-baryonic dark matter, and that is either WIMPs or primordial black holes. And there's no evidence yet for WIMPs. Now, for a while, I was very interested in the possibility that the dark matter was population-free black holes, but not the primordial ones, the first generation of stars. I'm going to skip over this slide. But I'll just say that I worked on that possibility for about 5 years, but I no longer take it very seriously. But most of the things which were actually attributed to population-free black holes are now attributed to primordial black holes. But there were 2 key exciting developments. In 1996, the people were looking for dark matter using microlensing. The idea was that you look at stars in the Magellanic Clouds, and you look for microlensing when a halo object goes in front of one of those stars, and it causes this microlensing effect. The luminosity goes up and then goes down, and the time scale gives you the mass. And in fact, the Macho project did find evidence for this, and it found evidence for machos of about 0.5 solar masses. And that was very exciting because that was precisely the sort of mass expected for PBHs that formed at the QCD phase transition. And there were reasons to think you could form primordial black holes then, because the pressure is reduced, which means you expect to form PBHs. So for those of us who worked on PBHs, that was very exciting because we thought we found them. Unfortunately, later it was found that the fraction of the dark matter could only be about 20%. That's what the Macho project itself concluded. However, they were assuming a certain model for the rotation curve of the galaxy, assuming a flat rotation curve, whereas now we know it falls down. So nowadays, some of my colleagues at least argue that they did in fact find the dark matter, but even though it doesn't seem to have all of it because you have an extended mass function. But the really the key factor which developed interest, reduced the interest, was of course the detection by LIGO in 2016 of the merging black holes. Since then, of course, the LIGO, Virgo, CAGRA project has found nearly 100 of these merging events. And what is interesting is that some of them seem to be in a range which would not be explained by normal stellar collapse. And so it's been suggested that some of these could be primordial black holes. This isn't the mainstream view among the LIGO people. However, there are at least, you go to PBH meetings, and this is a key interest, whether some of these events are primordial black holes. Now, I'm going to miss out this. This is just a statement about constraints on primordial black holes. For a long time, until about 2016, most of the emphasis was on how you could constrain primordial black holes. And there were all sorts of constraints on the fraction of the dark matter, which could be in primordial black holes of various mass ranges. Let me miss out this because I'm running out of time. But what I want to end on stressing that in recent years, the emphasis has shifted from getting constraints on primordial black holes to actually arguing that we have got evidence, positive evidence for them. The evidence is not conclusive, but at least it's something which a lot of people are working on. So I've just quoted a paper here, which is with my colleagues Sebastian Claes, Ryan Garcia-Bellido, Mike Hawkins, and Florian Kuhnel, and we've written this paper, Observational Evidence for Primordial Black Holes, a positive perspective. This is named after the positivist philosophy movement about 100 years ago, which says that you should always focus on what you can observe. And so what we've claimed, and not us, only us, but quite a number of other people,